Thanks very much, Joe. I'd like to reiterate that welcome and just introduce our first speaker, Professor Anna Marie Roos from the University of Lincoln. She's going to tell us about deconstructing the Copernican and Galilean controversy within the Catholic Church.
Good morning, everybody. Thank you for that nice introduction, and it's a real honor to be here today and be back in Oxford. So the premise of this talk is that the feud of Galileo, Copernicus, and the Catholic Church has been overblown, or at least fairly mischaracterized in popular treatments of history. In the latter case, we'll see some of the feud was brought by Galileo himself. Just a little note here that Copernicus's book that promoted a sun-centered universe, or a heliocentric universe from helios, for the Greek for sun, versus a traditional earth-centered universe, or geocentric, was only condemned by the Church 70 years after his death. The Copernican and Galilean controversies were thus not solely about the Church versus science. Based upon the instrumentation of the day, an earth-centered or a sun-centered system were equally plausible in the 17th century and able to explain observed astronomical movement. So first, I'm going to discuss the geocentric system of Aristotle and Ptolemy, and Copernicus's attempts to reform it. Finally, I'm going to explain why Galilean dynamics and astronomy was suggestive, but ultimately inadequate to prove a sun-centered universe and moving Earth at the time he was writing. And we'll talk a little bit about Galileo's hubris. He was a genius, he knew it, and you're going to see he had an ego the size of Florida. Since the 13th century, the Catholic Church had integrated a very uneasy synthesis of Aristotelian cosmology, which was the structure of the universe, and Ptolemaic astronomy. Cosmology really does concern, at this time, just the physical structure of the universe, and astronomy was part of what we call the quadrivium, or mathematical disciplines, and it plotted where and when the planets were. Essentially, astronomy was a calculating device. So let's go first to Aristotle's cosmological theory. It was first discussed in De Caelo on the heavens in 350 BC. This is a diagram for Peter Apian's Cosmographica in 1524. So you can see just from that, Aristotelian cosmology was prevalent for centuries and centuries and centuries, really until Copernicus. Now, he claims that the heavens have two distinct areas. The sublunar one, which is below the moon, you can see there, and the Earth is at the center here. And the Earth is surrounded by elements of water, air, and fire. The Earth, which was made of the very heaviest Earth element, rested immovably in its natural place at the center of the sublunar region. The watery sphere that surrounded that of Earth, but the boundaries between the two were a bit irregular because the higher parts of the land projected above the oceans which surrounded our globe. The sphere of the air was next, or our atmosphere, and above it, but below the moon, was a sphere of fire, which was the lightest of the elements and the transition to the eternal realms of the planets. So they did really believe that there was a sphere of fire above the air. You might say, well, why didn't we see flames in the air? Well, that was because the element of fire was thought to be transparent. If any of you read Dante, you'll know that Dante and Beatrice, when they're traveling to the moon, they actually go through the sphere of fire, and Dante describes it very beautifully. The sublunar realm was a realm of change and corruption. Each of the elements were constantly displaced from their spheres by the motions and influences passed down from the prima mobile, which we see there at the top, outer sphere. That was Aristotle's term for the sphere of rotating stars in the sun. So the stars were really thought to be in a wheel that moved around us. And if you look at the night sky, they really do appear to be doing that. They were thought to be a little over 1,000 at the day because that's what we could only see with the naked eye, and the universe was bounded, was not infinite. The earthly region, in turn, was surrounded by the orbs of the moon, sun, and the 5 planets, because those are the only ones that were known, as well as the prima mobile and what was called the crystalline and empyrean heavens. The heavenly domain, beginning with the moon and extending upwards to the celestial heaven, was considered perfect and unchanging. It was composed not of earth, air, water, and fire, but a special 5th element called the ether, which was perfect and shining and noble. Aristotle was absolutely convinced that the celestial ether was incorruptible and it composed unchangeable heavens. He posited that the planetary orbits were solid crystalline spheres made of the ether, to which the perfectly polished planetary bodies, also made of the ether, were firmly attached. Now you might say to yourself, well, okay, so I'm looking up at the moon. yeah? And it doesn't look perfect to me. It looks like there's spots, there's macula all over it. Well, Aristotle said, oh, he said that's because it was sort of in that halfway house between the imperfect and the perfect. And so it had areas of denser ether and rarer ether, and the denser ether was the spots. Now, I call that a bit of hand-waving, but it seemed to suffice at the time. The ether, like earth, air, water, and fire, determined the movement of the object it composed. And this is what's really interesting about Aristotelian physics. It's not based on mass, like we think of as quantitative. It was primarily qualitative. The composition of the element determined how it moved. Isn't that interesting? Aristotle believed that the composition of a body decided it's what he called its natural motion, the motion which it would undergo spontaneously without any external force. Everything moved had to have a mover. There's no concept of inertia in Aristotelian physics. Natural motion could be linear or it could be circular. In the case of earth, air, water, and fire, their natural motion was either up or it was down, from to or to center of the earth. Fire and air were thought to rise naturally. Air goes up to the atmosphere, its natural motion was upwards. Aristotle said a candle flame, the fire of the candle flame seems to want to go upwards to that sphere of fire that was up there, as candle flames pointed upwards. Water and earth, however, were thought to fall naturally due to observations of rain going to the oceans and rivers, and simply gravity. If I would drop this prompt here, which I wouldn't do, I would say it's made of the earth element. It would go down to its earth, right down here to its natural place. It would fall naturally downwards. Natural motion. Aristotle thought, however, there was in addition another type of body whose natural motion was circular, nobler, and eternal. He concluded bodies to which circular motion were natural were to be identified with the ether, of which the heavenly bodies were composed. So the heavenly bodies are made of ether, the natural motion is circular, that's why they move around us in circular orbits. Now, in the second book of On the Heavens, Aristotle also argued that the shape of the heavens must be spherical, as the circle was the primary shape in nature. Once he's established that the shape of the planetary orbits were circular, he had to provide an explanation for the motion itself. He conceptualized what we think of God as an unmoved mover that functioned as an object of love and desire for the soul that animated the body of the outmost sphere of the fixed stars, the prima mobile. The prima mobile rotated at an enormous speed every 24 hours and communicated its motion to the planetary orbital spheres. Later, Catholic thinkers like Aquinas called this unmoved mover God, and that's how they incorporated it within the Christian tradition. That's why it lasted so long. Although Aristotle's Earth-centered cosmology explained why the planets moved, it did not explain where the planets would be at any given time. Aristotle's universe of nested spheres and uniform circular motion orbits also did not provide an explanation for what we observe the planets to move as. The planets actually don't go above us in a purely circular motion. They actually appear to us to loop or do a retrograde motion. So this was a bit of a conundrum. So if you wanted to explain how the planets moved actually, or at least a mathematical model of how you thought they moved, you didn't look at Aristotle. That's cosmology. You turned to Ptolemy. You turned to astronomy, which told you where the planets were at every given time. And you looked at his Almagest, translated as his great book, which was written in 150 AD. This is a little animation of how Mars appears from the Earth to move. It moves in this loop. It seems to go ahead of us and then behind us, and that's called retrograde motion. The Greeks called it a hippopede, or a horse fetter. The term planets actually comes from the Greek planetes, or wanderers, and retrograde motion, however, is only an apparent change of the movement of a planet through the sky. It's not real, and that the planet does not start moving backwards in its orbit. It just appears to do so because of the relative positions of the planet and Earth and how they're moving around the sun. Let's see if this GIF works. Here we go. No expenses were spared on this GIF. All right, so we can see here that the Earth is moving around the sun here, and the red is Mars. And as this repeats, what you're going to see, as it loops around again, at this point, the Earth looks like it's parallel to Mars. Then it appears from our viewpoint that Mars is behind us because this is a different orbit. And then Mars appears to be ahead of us. And if you want to plot it, if you don't believe me, you can actually do this on this diagram here, where the blue is Earth, The red is Mars. You can see they're parallel here. It's position 1. Mars appears to be ahead of us. Position 2. Mars appears to be parallel again. Position 3. Position 4 a little bit behind us, and then a bit more parallel. And so we can sort of track its motion across the sky. So how was Ptolemy going to explain this? It's explained really beautifully by a sun-centered system. But if you use an Earth-centered system, how is he going to do it? Well, he accepted the following order for celestial objects in the solar system. Earth at the center, Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn. But he realized, as had an earlier thinker called Hipparchus, that the inequalities in the motions of these heavenly bodies necessitated a mathematical system involving 2 constructions, deferents and epicycles. In this way, we could account for the movements in terms of uniform circular motion. So another gift, no expense spared. All right, so we have Earth at the center here, and the outer circle, the one in yellow, that is called the deferent, the big wheel, and we have Mars out here. And the little wheel is called an epicycle. Now you can see here in this mathematical construction that not only does Mars revolve on the big wheel, the yellow bit, the deferent, but it also at the same time loops around a smaller circle called the epicycle. If you're having trouble visualizing this, you can think of this as when you're on the London Eye, okay? If you're on the London Eye, and the center, where the Earth is sort of the pivot, and you're in a carriage on the wheel, if you just had the deferent motion, you just go around it in a circle, yeah? But let's say something malfunctioned with the London Eye, okay? And you're in the carriage, and instead of the carriage being steady, carrying you around this way, there's something wrong with the axle of the carriage, and it also rotates as you're going around, like this. All right? That would be quite a wild ride. But what happens as a result of that is that the planet appears to loop around, okay? So in Ptolemy's mathematical construction, right, he could vary the size of the deferent, he could vary the speeds of the rotation of the epicycle in the deferent, and he could add more epicycles. And he could, by a combination of circles, create curves that mimicked the actual path of planets across the sky. Now, as Ptolemy's naked eye observations of the stars were pretty accurate, the tables in his Almagest were very readily accessible, and his system of epicycles provides a model to predict planetary movement. His system really dominates the ancient world. And this is the model that both Copernicus, with his sun-centered system, and Galileo, who spent his career studying motion and positing the motion of the Earth, had to disprove. And that was a really tall order. So here's Copernicus. This is a portrait from the town hall in Turin. He was from the area we now know as Poland. Copernicus was, I guess I could best describe him, he wasn't just a graduate student, he was a gradual student. He was in school forever. He had a very wealthy Uncle Lucas who funded his study because Lucas wanted a personal physician around him and sort of a learned attendant. And so he sent Copernicus. Copernicus spent quite a lot of time in Italy. And Copernicus, in being Italy, this is the height of the Renaissance, he's looking at the works of the ancient Greek astronomers, and he got particularly interested in the work of Pythagoras, and this becomes important for a reason I'll explain later. So, in 1543, the year he died, Copernicus published this book called the De Revolutionibus, on the revolution of the heavenly spheres. And it's really been very much a traditional benchmark for the determination of medieval conceptions of the universe. The introduction of heliocentrism, or sun-centered system, shatters this distinction between the corrupt earthly sublunar realm, with earth, air, water, and fire being mutable, and the perfections of the heavens and its ether, which had been established by Aristotle and popularized by Ptolemaic astronomy. There's a really good author by the name of Edward Grant who did a book called Planets, Stars, and Orbs. I highly recommend it if you're interested in this. He said, by making the Earth just another planet, Nicholas Copernicus hurls an implicit challenge to the concept of incorruptibility. As a planet, the heretofore imperfect Earth was as perfect as the other planets, or conversely, the previously perfect planets were now as imperfect as the Earth. So, why did Copernicus make the decision to support a sun-centered universe? Well, remember when I mentioned before, he got very interested and he was a student in Pythagoras. He revives what he thought were ideas of Pythagoras. In the 16th and 17th century, Pythagoras' teaching were seen as is actually a return to the ancient wisdom, the sapientia, the basis of truth. The Pythagoreans were a sect in 6th century BC of Greek mathematicians. They believed that all of the universe could be explained by mathematical laws. And when Copernicus studied Pythagoras, he thought the Pythagoreans said that the universe was sun-centered, that the sun was at the center of what we now know as the solar system. And that spurred him to do the De Revolutionibus. It was one of the reasons. Unfortunately for Copernicus, the Pythagoreans said no such thing. The Pythagoreans actually said that there was a central fire at the center of the universe, and the Earth and the sun moved around that central fire. So this is one of these historical mistakes that leads to a great breakthrough. And history of science is like that. It happens all the time. So he had a mistaken interpretation of Pythagoras that led him to adopt the heliocentric system. Another thing he realized is that a heliocentric system would solve the problem of retrograde motion without the need for epicycles. So here are two of our magnificent gifts here. And we have the system of Ptolemy's on the left, where we have to use an epicycle and a deferent. But Copernicus realized if we had a sun-centered system here on the right, when it comes up, we don't need those bloody epicycles anymore. And it seemed to him to be much simpler and much more beautiful. And in fact, aesthetics plays a huge role in the revolutions of heavenly spheres. He actually writes a really impassioned encomium to the sun in his work. In the center of all, he says, rests the sun. For who would place this lamp of a very beautiful temple in another or better place than this where from it can illuminate everything at the same time? Beauty in science is important. It is. Scientists are very interested in simple, beautiful mathematical laws, so it does play a role. Now, we would think that such a very beautiful system would be accepted immediately, right? Well, in the first 7 decades following the publication of Copernicus' De Revolutionibus, there was almost no rejection of heliocentricity on religious grounds, not at all, because it was a hypothesis. He said this is possible how the universe could be. But there was very little acceptance by astronomers because of the substantial scientific problems the theory entailed, problems associated with the physics of a moving Earth. It was about the physics that was problematic. Now, what problems did 16th century and 17th century astronomers have with the Copernican theory? The first thing is Copernicus postulated that the orbits of the planets were purely circular, just as Ptolemy did, just as Aristotle did. However, in 1609, an astronomer named Johannes Kepler actually showed they're not. They're actually elongated ovals or ellipses. Copernicus himself did not do very many astronomical observations himself. He relied on Ptolemaic tables revised by a gentleman named Regiomontanus. People often said that if Regiomontanus wouldn't have fiddled, Copernicus wouldn't have danced. And so the Copernican tables offered a very only slight accuracy in predicting planetary positions over the Ptolemaic ones. So it's not really offering you a lot in terms of you just want to know where the planets are. He also offers very little physical explanation in the De Revolutionibus about how or why the Earth and the other planets moved, as the system was conceived before Newton's theory of gravity in the Principia in 1687. So when you look in the De Revolutionibus and you say, well, why do the planets move around? He says, well, they're spheres and they can't help but turn. That doesn't help you very much, yeah? Also think about it this way. If everything, gravity, things falling down, if something's falling down to its natural place, to an immovable Earth, and that explains why things fall down in Aristotle's system, what happens when you take that planet and you start it moving around? Why do things fall then? There's no explanation. Another thing that's very interesting is that if the Earth indeed moved, then astronomers should have been able to see something called parallax with regard to the fixed stars. So as the Earth moves around in our orbit, our point of view should be changing with regard to the fixed stars, producing an optical illusion of a change in their position. So stars should appear to move slightly side to side as the Earth revolves around the sun. One way you can do this is you can pretend that you're the Earth. You can put your thumb in front of your face. You can say, that's a star. You can pick any star you want to. It can be Betelgeuse. It can be the pole star, whatever flight fancy you have. And you can imagine, as you're in one part of the Earth, you're going around your orbit, from one part of your orbit, maybe perihelion, you're looking at the star from one point of view, and then from another point of your orbit, you're looking at it from another point of view. And if you experiment with this, and you just sort of wink and look at your thumb, what you'll see is this optical illusion of your thumb appears to move side to side. As it's close to you, that optical illusion is greater. As that's further from you, it's smaller. So a lot of astronomers said, well, okay, it's the Earth that's moving around Copernicans, why don't you see parallax? Well, parallax does exist. We do see an optical illusion, but what the astronomers in the 16th and 17th century did not realize is how far away the stars are from us. The parallax angle is very, very tiny, and you need a really powerful telescope to see it. We don't actually see parallax until 1838 with a powerful telescope. It's used to this day, however, to calculate stellar distance, just by a little trigonometry. And of course, we finally get to the biblical reason. You can see there's been lots of astronomical reasons. I mean, there's an important biblical reason. The Lord commanded the sun to stand still in Joshua 10:12. And if the sun wasn't moving, how could the Lord command it to stand still? So that's important. But it's only one reason of many that Copernicanism really was a mixed bag. Sense experience is also important. The Earth doesn't feel like it's moving. It moves very fast. It spins and rotates at the speed of 1,000 miles per hour, and it orbits the sun at a speed of about 67 miles per hour. I can put miles in kilometers because I'm American and we like imperial, so sorry about that. We don't feel any of this motion because the speeds are really constant, and the spinning and orbital speeds of Earth stay the same, so we don't feel the acceleration and deceleration. But they didn't know that. It seems to stand still. Okay, so it's a really mixed bag with Copernicanism. It solves retrograde motion beautifully. It's very aesthetic. However, it doesn't explain why the planets move. It doesn't explain the lack of parallax. It doesn't explain the biblical problems. It doesn't explain why we don't feel like we're moving. Hence, we have this gentleman come into the scene, Galileo. Now, Galileo dates are 1564 to 1642. This is the bust of him at his last home, the Jewel at Arcetri in Italy. He was an Italian astronomer. He was a physicist. He was an engineer. He sometimes described it as a polymath, and he was a great genius. In 1610, he published a very important work called the Sidereus Nuncius, or the Starry Messenger. You can think of it as a papal nuncio, as a messenger, if you want to sidereal a star. And he observed with a telescope. He did not invent a telescope. He designed a telescope based on an early invention by a Flemish man named Lippershey. He observed with a telescope, first with a 9-power one, then with a 15-power one, very simple, concave, convex lens in the tube, that Jupiter had its own moons. He saw that Venus appeared in phases, similar to those of Earth's moon, which suggested that Venus orbited the sun. And when he also pointed his telescope at the sky, he saw there were multitudes, more stars revealed with the telescope, which contradicts this idea of a fixed sphere of stars bounding the universe. Here he is with his telescope, this apocryphal drawing, showing it off to the Venetians. Ooh, great, they can see the stars. The Venetians were really probably more interested in this telescope because, they're a maritime republic in this period. They also invented naval insurance. They wanted to use that telescope to see which ships coming over the horizon happened to make it safely into port and weren't pirated, so that the insurers could cash in on their bets, essentially. And Galileo got a very nice lifetime pension from the Venetians for that invention. This is an example from the Sidereus Nuncius, a page from it, and there's a wonderful astronomer called Ernie Wright. You can see here, these are the moons of Jupiter. It's Jupiter with the little dots around it, the moons, and Ernie actually trained his telescope up there to see how accurate was Galileo in his observations of the moons of Jupiter. And he was damn accurate. And it's incredible considering he had about a 15-power telescope and probably not a great, that's difficult to do. Naked eye observations, this is really hard. And Ernie actually plotted, you can see Jupiter here with the moons of Io, Europa, Ganymede, and Callisto relative to Jupiter. And this thing is, you can see how Galileo's, the asteroids are the moons, and the circle here is Jupiter, because he's dealing with typographic symbols in his book. And Ernie went ahead and reproduced these observations that Galileo did from 7 January to 2nd March 1610. He did 64 observations of positions of these 4 moons, and they're absolutely spot on the money. So this is not to take away from Galileo's achievement. He also looked up at the moon, pointed his telescope up there, and he did not see a perfect shining sphere whatsoever as areas of rarer and greater density. He saw a jagged moon, nothing like that big of a crater on it. That was exaggerated by effect for Galileo to make a splash, but he sees rugosities and mountains and things on here. Later after the conference, there will be a set of PDFs on the website. I have a little sheet in there how Galileo calculated 1 mountain on the moon was 4 miles using a very clever combination of observation and trigonometry, and you can look at that. So this seemed to suggest that the Earth was nothing special, that the other planets were sort of like other Earths, and it seemed to, again, shatter this distinction between the sublunar area and the heavenly perfect area that Aristotle had suggested. That seemed to be a bit dodgy, right? Okay, this also shows you, this is Galileo's sketch of the stars in Orion's belt and sword, compared with the modern day photograph of the right. Galileo realized very quickly that we probably may not have a bounded sphere of stars that rotates around us, that perhaps of that bounded universe that Aristotle had postulated was infinite. All these things are extremely suggestive of a heliocentric system and a more infinite universe, but they don't prove it, because Galileo did not have proof that the Earth moved. Not yet. And that's something he worked on for the rest of his life. We also have to consider this, that there was another rival planetary system that was around at the time of Ptolemy and Galileo, or Galileo and Copernicus. Tycho de Broglie, 1546 to 1601. He was a Danish nobleman. He's surrounded here by all the coats of arms as his ancestors. He was a very impetuous gentleman. Yes, he did have a gold nose. He got it cut off in a duel with another astronomer who he was fighting over rival theories. And Tycho had a really ingenious solution to these problems of the solar system. He postulated what we call a halfway house system. Now, he said that it's geocentric, the Earth is at the center. But rather than having all the other planets, including the Sun, go around the Earth, as in the Aristotelian or Ptolemaic system, what he did is he had the Sun go around the Earth, but all the other planets going around the Sun. So he sort of combines the two together. Now, what advantage did this give you? Well, first of all, for a lot of Jesuits and church authorities, Tycho's system does not contradict Scripture. The Earth is standing still. It preserves Aristotelian physics, because things still fall to the natural place to an immovable Earth. It explained retrograde motion without the need for epicycles. It explains the absence of observed parallax, because the Earth is stationary. And Tycho's data was extremely accurate. He was the best naked eye astronomer before the invention of the telescope. So a lot of church authorities accepted this one. They said, this is the one to go. Again, we're dealing with astronomy, mostly. Some religion, but astronomy. So these are important steps down the road to heliocentricity, but none of these discoveries were definitive proof of heliocentricity, but they refuted significant aspects of the accepted Aristotelian cosmology and Ptolemaic geocentric astronomy. But Galileo does not want to compromise. He wants to establish heliocentricity. So, the trial of Galileo, and this is after, I've come to this conclusion after long talks with a lot of historians of science, and one wonderful guy named Tony Christie, who runs a wonderful blog called Renaissance Mathematicus. I'm always a little bit hesitant to recommend blogs, but this one is extraordinary. The trial of Galileo has been traditionally presented as this classic confrontation between the superstitions of religion and the innovations of science and truth. And it's true, absolutely. The Inquisition, they condemned Copernicanism as contrary to Holy Writ. They do bring Galileo to trial for the publication of a work called The Dialogue of the Two Chief World Systems in 1630, in which he supports heliocentrism. But to state that the Catholic Church was anti-scientific, and dogmatic, and Galileo was a defender of truth, is simplifying the historical events to an absolutely huge degree. First thing I want to say is the Catholic Jesuits were not superstitious. They were some of the best astronomers of their day in the 17th century. Christopher Scheiner's a shining example. He discovered sunspots, although Galileo tried to take the credit away from him. And Galileo, for a lot of his career, enjoyed tremendous patronage from the papacy and esteem. But I will say, Galileo had a very abrasive personality. He made enemies very easily, and his actions before the trial may have led to the dispute occurring in the first place. So he has very influential friends within the church. They include Cardinal Maffeo Barberini, who becomes a future Pope Urban VIII. They're very much aware of the situation I've described, where there's an open debate of the validity of Copernicanism. And they warn Galileo to proceed with caution. They tell him, if you treat Copernicanism as a hypothesis and you want to discuss it as an astronomical model, that's cool. But if you want to discuss it as physical truth, buddy, you better have the physical proof that the Earth moves. And that was the condition. Galileo, I think, ignored this very sensible advice, and the matter came to a head with something called a letter to Castelli, which was later published as a letter to the Grand Duchess of Christina, which is one of Galileo's patrons. So this is a letter here that's published in Florence, Tuscany. So there's a story with this. So late in 1613, there was a newly appointed professor of mathematics at the University of Pisa who called Benedetto Castelli, and he was a pupil of Galileo's. And he attended a lunch hosted by the Grand Duchess Christina, who had been one of Galileo's patrons. And Christina sort of expresses some doubts about Galileo's observations of the moons of Jupiter, and she considers the Copernican astronomy possibly heretical. So after the meal, she summons Castelli to her chamber, and then in the presence of other guests challenges him about these ideas of the mobility of the Earth. Galileo heard about this, got rather incensed, and he writes this very long letter to Castelli, supplying him with arguments to use against those quoting biblical passages against heliocentricity. Now, it's very interesting. The original holograph of this letter is in Britain. You would think it would be in Italy. We thought it was in Italy for a long time. It's in the Royal Society Library. We don't know how it got there. This is an open research question, actually. The mistake came about because the letter was misstated in an old catalog. And a young postdoc named Salvatore Ricciardo, very bright young man, saw this and realized, this is misstated. My God, this is the original letter. So any of you out there who want a PhD thesis, there you go. You can go look at this. You can go see it if you want to. Go talk to Keith Moore. He'd be very happy to show it to you. All right. So in this letter to the formal pupil Castelli, a Benedictine monk and professor of mathematics at Pisa, Galileo sets forth his ideas on the relationship between science and religion. And it's a very short treatise in epistolary form. It's done as a letter because this is a period of the Republic of Letters. People didn't just write letters like private emails. They published sort of these very rhetorical letters to each other to argue a particular point of view. And the first scientific papers that were published in things like the Philosophical Transactions of the Royal Society were actually letters. So this is quite normal. The letter to this circulated very privately and widely, and it was designed to offer a response to objections from Aristotelian philosophers and theologians who regarded Copernican astronomy as a serious threat. And the opponents were very convinced of the incompatibility of the new astronomy with some passages in the Bible. Now, in order to support Copernicus's view and the freedom of scientific research, Galileo maintains a very clear-cut distinction between the realm of faith and that of scientific knowledge. And this is Salvatore Ricciardo's here, his words. He argues that the statements of the Bible about natural phenomena did not constitute valid reasons for drawing corresponding scientific conclusions. Galileo's argument, which was later set up much more systematically in the letter to the Grand Duchess Christina, Ricciardo says, marks a crucial step in the rise of modern culture since it claims the autonomy of science from the control of theological authority. And we see that, we go, hey, Galileo's a big hero for saying this. But that's not the way the church saw it whatsoever. You look at a theologian like Paul V. He said, if we're going to accept heliocentricity, then we have to abandon a literal interpretation of this and other passages in the Bible. And we are only prepared to make that concession if there's solid empirical evidence that the sun is at the center. Now, why was this sensitive? Think about the time with Galileo's writing, 17th century. What has happened to the Catholic Church in the past 2 centuries? The Protestant Reformation. The Protestant Reformation is a direct challenge to the Catholic Church's authority and its ability to interpret theology. And the Catholic Church is doing the Counter-Reformation. It's going against what Martin Luther had to say. So, of course, it's more sensitive at this time to critiques. So, the letter, when it comes out, triggers a 1616 suspension of Copernicus's De Revolutionibus, and it leads to Galileo being warned by Cardinal Bellarmine, one of the leading figures of the Inquisition, and a really outstanding Jesuit theologian, to abandon Copernican astronomy. And the Pope tells Bellarmine to inform Galileo of the Commission's judgment and forbid him from holding or teaching the heliocentric theory. The theory, heliocentricity is a statement of fact, was forbidden, but not the hypothesis. You could talk about his hypothesis any way you wanted. And that was a very important distinction. And here's the prohibition of Copernicanism on the 5th of March, 1616. I always remember that 5th of March is my birthday, so hooray for me. And it says that the Copernicus' work has to be suspended until corrections. That meant there were a few sentences in it that they found that were problematic, but they didn't condemn the whole book. Okay. So now we'll get to the trial of 1633. So Galileo's admonition stops the Copernican movement dead in its tracks, and he busies himself with other things. He tried to find a way to solve the problem of longitude, for instance. But in 1623, he received some very hopeful news. This guy, Maffeo Barberini, had been elected Pope as Pope Urban VIII. He had a fairly positive view of the arts and sciences. He was considered quite enlightened. And writing from Rome, the Pope's private secretary urged Galileo to resume publication of his ideas. And in the early part of his reign, the Pope has very long audiences with Galileo. They discuss things in the papal gardens. They talk about astronomy, they chat about physics, they chat about Galileo's telescopic redesigns. And Galileo was very encouraged by a Pope who seemed open to renewed debate and the merits of the Copernican system, so long as the arguments fell short of purporting to be a definite refutation of the Earth-centered universe. And Galileo is encouraged to begin work on a book that eventually will prove his undoing, the dialogue concerning the 2 chief world systems. Now, on 24th December 1629, he tells friends in Rome he's completed work on this dialogue on the 2 chief world systems. It's been described as the story of the mind of Galileo. It marshals all his arguments together for a sun-centered universe. It was a book for the educated public, not for specialists. It was written in a dialogue form. Why? It was an imitation of the Socratic dialogues way back when in the ancients, and to allow for free debate and discussion. Only 2 systems appear in the dialogues, the Ptolemaic and the Copernican. Tycho's system mysteriously is not there. Why? It offered a really good alternative and a really powerful argument about Galileo's promulgation of heliocentrism. He just leaves it out. Galileo inserted statements about the hypothetical character of the work in the preface and the conclusion, but it's not even-handed. And I would say it's very contrary to the instructions he was given by the Church to only discuss heliocentrism as a hypothesis. There's 3 Italian gentlemen in the book. Galileo uses a variety of arguments to lead his readers to accept Copernican theory. There's a character, Salviati, who is Galileo himself, a person described as supreme intellect. There is Sagredo, who is a Venetian nobleman, actually modeled after a friend of Galileo's, who's open-minded and hesitant to draw conclusions, who's a good listener. And then there's Simplicio. He's a straw man. He's a stubborn, literal-minded defender of the Earth-centered universe. Okay, and here's the frontispiece. These are not the 3 Italian gentlemen, confusingly enough. They're actually Aristotle and Ptolemy and Copernicus. Aristotle's on the left, Ptolemy is holding an Earth-centered armillary sphere, and Copernicus has a sun-centered model of the universe, and they're having this discussion. Okay? All right. Now, early news from Rome gives Galileo reason for optimism that his book would soon be published. It has to go through a chief licensor, Niccolo Riccardi. Riccardi says we can, take care of any theological problems with it. And when Galileo arrives in Rome in May 1630, he writes, "His Holiness has begun to treat of my affairs in a spirit which allows me to hope for a favorable result." Urban VIII reiterates to him, though, if the book treats the contending views hypothetically, not absolutely, we can publish it. And Galileo says, oh yes, of course. All right. Well, Galileo was, I think, a bit confident that he was going to win the day because he had what he called his secret weapon. He thought he had a theory of the tides that absolutely proved that the Earth moved, right? He was very inspired by the behavior of water when boats come to a halt. And he thought that the ebb and the flow of tides resulted similarly from the acceleration and deceleration of the oceans, sort of sloshing around. How did he say this? Well, he said that the tides were propelled by the dual motion of the Earth around the sun and around its own axis. And he said that because the direction of rotation of the Earth's annual and daily movements are the same, the speeds accumulate on the side of the Earth turned away from the sun. And he said the opposite happens on the side facing the sun. And between these points, the seawater is accelerated or deaccelerated, just like the water in the barge. The problem was with Galileo's theory is, other than it's wrong, is the tide, in his theory, the tides only occur once a day instead of twice. But he thinks that this is the secret to proving the Earth's motion and thus a heliocentric system. But he still really doesn't have definitive proof of a moving Earth. We know it's because of gravity, right? And this is from the National Observatory of Atmosphere in the United States. And we know it's really high tides and low tides. As the moon's position changes, two tidal bulges rotate around the Earth. The bulges represent high tides, while the corresponding flat sides indicate low tides. But again, Galileo's pre-gravity, pre-Newton. So it was realized soon after the book was published in February 1632. It sold out very quickly. It became the talk of the literary public. But it was realized very quickly it was a very thinly veiled brief for the Copernican model. And orders come down from Rome to suspend publication of the book. On 5th September, Pope Urban told Francesco Niccolini, "Your Galileo has ventured to meddle in things that he ought not, and with the most grave and dangerous subjects that can be stirred up these days. Jesuit enemies have Galileo, because he didn't make friends easily, convinced the Pope that the dialogue was just a thinly veiled brief of the Copernican system, and they also convinced him that the Pope's own arguments for physics, and particularly concerning the tides, were put into the mouth of the simple-minded Simplicio. And the Pope thought that Galileo was ridiculing him. Okay. So what happens? The trial. The boom is lowered. Now, we think of the Inquisition as people being thrown in the dungeon and chained and being tortured, and that did happen. They didn't treat Galileo like that. He was getting elderly. They showed him the instruments of torture, but they never tortured him. They wanted to frighten him. The Inquisition was actually very much of a judicial court. It was very procedural, right? So the Inquisitor of Florence showed up at Galileo's house and said, here's your summons. Present yourself to the Holy Office in Rome within a month. He goes to Rome. You can see there's a bit of a delay. He takes a little longer than a month. He has lots of excuses, but he eventually gets there. He surrendered to the Holy Office, and he faced Father Fronzuola, the Commissionary General of the Inquisition. And the counselors of the Inquisition look at the dialogue in the two chief rule system, and they prepare a 7-page evaluation. They conclude that Galileo in the book taught, defended, and showed that he held Copernican theory, and that while he claimed to discuss world models hypothetically, he gave the Copernican model a physical reality. He was sentenced on 22nd June 1633. He was released to the custody of the Florentine ambassador. Niccolini described Galileo, of course, as being extremely downcast over his punishment. Of course he was. He was transferred to Siena, and then he finally was placed under house arrest, and he moved into a small farmhouse in Arcetri. He grew blind there, and he died 9 years later in 1642. He didn't spend his imprisonment in a dungeon. He spent it in a rather pleasant villa called the Jewel, but it was still house imprisonment, so I'm not making light of that. He was near his daughter, who ironically was a nun, a illegitimate daughter, and she'd visit him. So I hope that this talk shows you that it wasn't a fait accompli that the Copernican system would be readily accepted. And the interpretation that Galileo's trial was a matter of an ignorant church in conflict with the heroic science was simplistic. With the publications of his Principia in 1687 and the theory of universal gravitation, it was finally explained how the planets moved around the sun, the correct interpretation of the tides, and the acceptance of the heliocentric system. Thank you very much.
Thank you very much, Professor Roos. We now have a few minutes for questions. Would you like to take questions from?
Oh, sure. I can take questions. Sorry,
Okay.
I didn't know you wanted to do here. Yep, I'm happy to take questions. Please go ahead. Yes.
Is it a myth that his trial he did retract his views on heliocentrism?
Oh, yes. If you acted your views and recanted your views, it was actually could be punishable by death if you did that. That's what happened to Giordano Bruno. So it's a complete myth. He would have been very stupid to do that. Yeah, absolutely.
What's the evidence that he knew about Tycho's model?
Oh, he knew about Tycho's model, absolutely. And I'll tell you why. He had an active correspondence with Johannes Kepler. And Kepler, of course, for a while worked for Tycho Brahe. So he knew about Tycho's model. Sure he did. He just didn't cover it because it contradicted his own desire to promote heliocentrism. But in fact, if you want to read some beautiful correspondence, do look at the stuff between Galileo and Kepler. There's this wonderful meeting of minds between the two as they discuss astronomy. And I mean, as we know, Kepler did the planetary laws and elliptical orbits and equal area sweep out equal times. And Kepler actually had it wasn't gravity, it was still, he imagined the sun is putting out almost like an invisible broomstick of force and pushing the planets around it, yeah. But I mean, it's beautiful correspondence. But oh yeah, Galileo knew about Tycho very well. Sure he did.
Did this letter and the statement that maybe you should first look at the book of nature before you consult scripture on such matters, did that play any role at all in the trial?
Galileo.
What we see now as the basic conflict here.
Yeah. Galileo held that very privately. And in fact, when he was put in the custody of Archbishop Piccolomini, who was actually quite sympathetic to Galileo, they discussed such things. But it didn't play a formal.
I didn't have that at all.
Huh?
In the trial itself, there's nothing in the acts of the trial.
No, because the trial was very circumscribed. It was about purely did Galileo ignore the prohibition given him by Cardinal Bellarmine. Even that, there's some interesting historiography about that as well. Let me see if I can find it here. There's some debate over whether Galileo was told he couldn't hold, defend, and teach heliocentric hypothesis. Some people said that he was allowed to defend and teach it, but he couldn't hold it. So there's a bit of a problem with some of the evidence that the Inquisition presented. This is a big historiographic debate. You can look at Stillman Drake, and he talks a lot about that. He's a good author to discuss that problem. Yeah.
You mentioned that Galileo's book sold out. Do we know how many copies were printed and how many have survived? And also, why would the penalty for recanting your views be worse? Why would you only get death if you recanted?
Because once you swore that you would do penance in front of the Inquisition, if you recanted on your word and then went back to the other way, then it was seen as a direct contradiction to what they had given you. I mean, if you go down to the Martyrs' Memorial In Oxford, yeah, and you look at the Protestant martyrs that are there, some of them were killed because they had said that they would actually go back to Catholicism, and then they actually recanted their views later, and they were actually killed for that. Some of them recanted under threat of torture, of course. But if you recanted, then you were said not to be following what the church told you to do. So that was very serious. I don't know the precise amount of copies that were done of the Dialogue of the Two Chief World Systems. I know there are a lot of them that survive. There's one really good copy, and you can see it online. It's at the University of Oklahoma, if you can believe that. They have a wonderful library called the Bezel, and that one actually has annotations in it in Galileo's hand, as he's sort of thinking about some of the things that he wrote about it. So if you want to look at that, that's a really good one.
So next question is from the gentleman in the third row here. And I'm going to take one more after that.
You mentioned that this was a period when the Protestant Church had been formed. What was its position with regard to the...
Oh, the Protestants actually were very much geocentrists because, I mean, Luther certainly was, because the Protestants had a very literal interpretation of the Bible. But I think as time went on and the evidence started mounting up, then we start seeing a softening of this position that perhaps the Bible was speaking in parables. It was a long period of time from when Luther rebelled against the church in the early 16th century to the 17th century. By the 17th century, I think among educated Catholic intellectuals, they had no trouble discussing Copernicanism as a hypothesis whatsoever. And I think some of them secretly thought that it probably was true, but they were waiting for the definitive proof. Because, I mean, think about it. It's a big thing to overturn, isn't it? You have to really know before you're going to say that these biblical passages were just stories designed to educate the public rather than literally true. Yeah.
Thanks. So the last question is from a gentleman at the back left. So microphone guy has a bit of ground to cover, I was going to say.
Hi, thank you very much for the excellent talk. I was just, from this, I'm thinking, is one way that we can conceptualize this so-called conflict or episode in history as kind of institutional dogmatism versus young heresy, in the sense that it's not kind of science versus religion, but actually institutions that have political, economic, and social interests, and will protect them. Because if so, then we can apply that potentially to scientific institutions as well.
I think that we need to, it's a really good question and a good point. I think that we need to, all history of science, in my opinion anyway, needs to be set in social, cultural, institutional context. And there's a really good book by Mario Biagioli called Galileo Courtier, which I recommend if you're interested in this aspect of it. It really shows how Galileo was playing a game of patronage. I mean, there's no National Science Foundation or, European Union or whatever funding for natural philosophy, as they called it at the time. He wanted support and he wanted patronage. And it shows how, Biagioli really shows how Galileo was playing a game of patronage, and he didn't play it for himself very well at the end. Yeah, and so, yeah, you need to put this stuff in socio and institutional context, but I don't buy that the church was dogmatic. I buy that it was in a position where it was defending its authority, but if it was going to overturn a key precept of its authority, that was in fact being brought to the fore of intellectual thought by Galileo himself, by his actions, that there needed to be a really good reason to do it. I don't know if that helps.
Okay, great. Thank you very much. I think we ought to thank Professor Roos again for a wonderful talk. Okay, I'm delighted to welcome as our next speaker Professor Andrew Gregory from University College London. He's going to tell us about Democritus versus Aristotle. Are there atoms and empty space?
Thank you. I'm delighted to be here, and I'm going to talk about a feud in the ancient world between Democritus, who is usually reckoned to be the first atomist, and Aristotle, who denied that there are any such things as atoms or any such thing as a void for the atoms to move around in. So let me just set an overview first, because there are a couple of other people to talk about who are interesting in this context. Firstly, there's an ancient Greek philosopher called Parmenides, who lives around those dates. He has some entertaining views, we'll come to those in a minute, and the first atomists, Leucippus and Democritus, act very much in reaction to Parmenides, so that's probably the first feud. I want to talk a little bit about Plato on matter as well, as he has things to say about the early atomists, and then I'll talk a little bit about Aristotle. So, to start with, dear old Parmenides, he argued these things. It is not possible for nothing to exist. It is not possible for more than one thing to exist. Therefore, there is only one thing that it exists. It is not possible for there to be any change, and the one thing that exists is spherical. Why have I got a question mark here? People in the ancient world did not know what to make of this, and scholars right up to the present day do not know exactly what to make of this. Whether this is Parmenides' actual position is one issue. That he argued for this, that's undoubted. Why does he think there's only one thing? Well, if he's actually right about nothing does not exist, and what can you say about nothing? And that's a serious question. You know, is there anything you can say about nothing? And Parmenides thinks if you can't talk about it, it doesn't exist. Right? So that leaves you with what exists. So what exists? Can it be lots of things? Well, what separates the things that exist? It's not what doesn't exist, because that doesn't exist. Right? So that leaves you with this possibility that there is only one thing, and it is spherical. The spherical thing is an argument from symmetry, and he's quite specific about that. Let me then take you to the reply of Leucippus and Democritus. They say it is possible for nothing to exist, and that nothing is empty space or the void. So you now have what is, and they say there are many things that are. And those things are indivisible, literally in the ancient Greek, atomos, uncuttable. Right? So the first atoms are little Parmenidean worlds, and there are a multiplicity of them, and they move around in empty space. Change, according to the atomists, occurs because there is a motion of those atoms, and we see change when those atoms come together to form macro objects, or they come apart again just to be atoms. So this effectively is the first part of the feud between Leucippus and Democritus and Parmenides. The atomists want to assert, look, there is a void, and these little atoms move around in the void. Those atoms don't change at all. They're uncuttable, indivisible. Shape, size, and number of atoms. So this is a report we have on Leucippus's works. Leucippus supposed there to be an infinite number of atoms that are always in motion and have an infinite number of shapes. So in denial of Parmenides' idea that there's only one thing and it's spherical, Leucippus and Democritus believe there are an infinite number of atoms and an infinite number of shapes. So any shape and size you like. Bonding is purely physical, and it occurs by entanglement. So these atoms have all sorts of shapes and sizes, and if you can imagine some odd shaped atoms, they all cling together like that. Not cling in the modern sense of being attracted to each other, but they will actually just interlock with each other. And change at the level of human perception happens when enough of these atoms become entangled together to form a macro object which we can perceive. And again, those macro objects can come apart through motion and shaking around. This is Aristotle talking about Leucippus and Democritus. He says, being, they say, differs only in shape, arrangement, and position. A differs from n in shape, an from na in arrangement, and z from n in position. So there's this theme in Greek philosophy that there should be something that doesn't change. And for the early atomists, it's the atoms that don't change. That's why they say that being, Aristotle says here, that being only differs in the shape, arrangement, and position of those atoms. I quite like the graphic that PowerPoint threw up from this. There in the middle, you've got all these different shapes of atoms, all congregated together into a macro object, lots of little atoms moving around the outside. I think that's quite good as a vision of what Leucippus and Democritus thought the world was like at the micro level. They have quite a strong take on the nature of this world. So again, this is a fragment of Leucippus. Nothing comes to be at random, but everything for a reason and by necessity. Also important is this fragment from Democritus, who said, by convention sweet, by convention bitter, by convention hot, by convention cold, by convention colour. But in reality, atoms in the void. Right? So that's, again, a very strong thing to say. And it puts forward quite a strong, what's technically known as a reductive program. So what we see and perceive in our world, bitterness, temperature, colour, they aren't actually there. There's just atoms in the void. We're a set of atoms in the void. There's a set of atoms in void out there. We perceive those atoms in certain ways, but qualities like red or heat aren't actually there. It's just atoms in the void. So that sets quite a strong reductive program. I'll talk about that a little bit more later on, because Aristotle, that's one thing that Aristotle will want to object to. One question you might ask yourself is how strong the affinities are between what I've just described about Leucippus and Democritus and modern atomic theory. I think the first thing to say about Leucippus and Democritus is actually probably the first example of a two-level theory, where human beings have thought, okay, there's a macro world which we inhabit, there's also a micro world, and that micro world is actually radically different from the macro world. Let me talk a little bit about dear old Plato, who is also entertaining and intriguing on what makes up the world. Plato had a complex theory of atomism, where he has simple triangles which make up three-dimensional, inverted commas, atoms of earth, water, air, and fire. So the ultimate parts of matter for Plato are two types of triangle. Right? There's the 1, 1, root 2 triangle and the 1, root 3, 2 triangle. Right? These are the ultimate building blocks of matter for Plato. And you can fit them together like this. So there you've got your two basic building blocks at the top. The 1, 1, root 2 triangles form up in fours into squares like that. And then they can form up into a cube like that with 6 square faces. The 1, root 3, 2 triangles, 6 of them join up to form that sort of triangle, and 4 of them form up to form a tetrahedron. I was most amused about this overhead, which I admit to nicking off of Google Images, because Google Images nicked it out of one of my books. Oh dear, when Wikipedia first started, I was amused to find some of my lecture notes turning up on Wikipedia. Obviously, my students had copied them and sold them to Wikipedia. What's the next bit of Plato's matter theory? There are Platonic solids. These are the 5 Platonic solids known in the ancient world. What is special about them? They are made up of identical faces. So the cube is made up of 6 identical squares. The tetrahedron is made up of 4 identical triangles. What Plato wants to say is the cube is Earth. The icosahedron, 20-faced entity, is water, the octahedron, 8 faces, is air, and fire is the tetrahedron. And Plato's idea is, right, here we have the four earth, water, air, fire, the four elements of classical Greek theory. We can account for these by saying, okay, these are the shapes of their, inverted commas, atoms. Those atoms come apart into smaller constituents like that. The big question, why? Why has Plato put this together in this manner? If you ask Plato, he will say, these are the best, the simplest and most elegant. And he would say that although the world appears complex and diverse, there's an underlying order and a mathematical order, and that order is simple, elegant, and aesthetically pleasing. Let me just read you a little passage from Plato where he's describing these things. This we hypothesize as a principle of fire and of the other bodies. But the principles of these, which are higher, are known only to God and whoever is friendly to him. It is necessary to give an account of the nature of the four best bodies, different to each other, with some able to be produced out of the others by dissolution. You must be eager then to bring together the best four types of body and to state that we adequately grasp the reason for the nature of these bodies. Of the two triangles, the isosceles has one nature, the scalene an unlimited number. Of this unlimited number, we must select the best if we intend to make begin in the proper manner. If someone has singled out anything better for the construction of these bodies, his victory will be that of a friend rather than an enemy. We shall pass over the many and postulate the best triangles. Right? I think we get Plato's drift here. You know, we want the best ones. Okay, so Plato has what is known as a teleology, a sort of end-directed or good-directed account of nature. It probably is one of the passages where it comes out most strongly. I think an important factor here is that Plato thinks that when the origin of the cosmos happens, there is a chaos to start with. He then has his craftsman god fashion an ordered cosmos out of that. What are the criteria that craftsman god uses to create the world? Well, he uses the best criteria, the best tools for it, and therefore he must have reason for choosing certain shapes, particles, or whatever over the other, and that's why Plato phrases it in this manner. Let me try to just run a little bit of philosophy of science off of this. Think yourself back to when you did O-level chemistry and you were given an atom of carbon and 4 atoms of hydrogen and some rods to join them together. Right? You remember doing that? Right? What shape are the atoms? Spheres. Sir, you are an excellent Platonist. Why? Because you have chosen a mathematically simple and beautiful idea for the shape of an atom rather than follow Leucippus and Democritus and say they're all shapes and sizes. Now let's move on to A-level chemistry. And you are told about electrons, protons, and neutrons. What shape are electrons, protons, and neutrons at A-level chemistry? I see a lot of nodding, and I see a lot of further followers of Plato in this matter, because you all know they are spherical, are they not? Right? Behind that ancient world talk of Plato, I think there is this principle, and Professor Roos talked about it earlier on. For some people in science, beauty matters, and for Plato, certainly beauty mattered. And part of his feud with Leucippus and Democritus is precisely that. For Plato, he's going to say, there are a small number of mathematically well-defined ultimate parts of the world. Leucippus and Democritus are going to say, no, there are all sorts of shapes and sizes, and these things are at random. Plato will also say those small number of mathematically well-defined atoms are designed, and they are the best ones. Behind that is another row that occurs in the ancient world, and it's interesting to see this feud being resurrected in the 21st century. The early atomists thought there were an unlimited number of cosmoi. Cosmoi is just plural, ancient Greek plural for cosmos. Just cosmoses doesn't sound very good. Okay, so they thought the Leucippus Democritus thought there was an infinite void, an infinite number of atoms, and there are an infinite number of worlds or cosmoi within that void. And they thought those came about by accident. Our cosmos just has an order which we explain as part of an infinite array of these. Plato, on the other hand, says no, there is one cosmos, only one cosmos, there can only ever be one cosmos, and that has been well designed. Right? And that ultimately is an important physics feud between Plato and Leucippus and Democritus. Do we explain what we see around us in terms of a multiplicity of accidents, or do we see some sort of order, beauty, and design in the world? And Plato, of course, goes very strongly for the order, beauty, and design. Aristotle, of course, has criticisms of Plato. And the little illustration there, that's from the centre of Raphael's School of Athens. That's Plato and Aristotle having a debate. Quite what they're having a debate about, that's a different matter. Aristotle says, look, Plato, when you take the matter apart into planes, why do you just stop at planes? Why do you stop at triangles? Surely that's entirely arbitrary. And he asks a question that's puzzled philosophers ever since. What on earth are those planes meant to be made of? Right? Are they just geometrical? But geometry doesn't make up things. Are they meant to be matter? In case that's really puzzling. Why do they join up as regular solids? That's equally puzzling, as puzzled people since. Imagine you have those little atoms as icosahedra, tetrahedron, all the rest of it. What happens when the planes come apart? Does that mean there's a temporary void there? And Aristotle, as I'll say in a moment, is absolutely against the idea of any sort of void or vacuum. And Aristotle questions, okay, but do the solids pack together? Do they tessellate properly? Do they occupy all the space? Because if not, then there is empty space, and empty space is not allowed according to Aristotle. I'll come back to Aristotle's reason why empty space isn't allowed in a moment. Aristotle, 4th century BC, has an unparalleled influence. He's a great systematizer. It's very difficult to get rid of Aristotle's thinking because it's so comprehensive and so systematic. And I think it's only with the advent of René Descartes and his mechanical take on the world that Aristotle really gets superseded. There are debates about it, but nothing that really can take Aristotle's position. The theory of natural place, I think, is the key to Aristotle's thought, certainly within his physics, but that spills out into other parts of his thought as well. So, Aristotle on matter. Aristotle follows most of the ancient Greeks in saying, right, there are 4 elements, earth, water, air, and fire. And they are characterized by 2 pairs of opposites, wet and dry, hot and cold. So earth is cold and dry, water, cold and wet, air, wet and hot, all the rest of it. In principle, those elements can transmute into each other, and they can do so unproblematically. So I think Aristotle would, if an alchemist came up to Aristotle, I think Aristotle would scratch his head and say, what on earth are you talking about? What's the problem? Of course, earth, water, air, and fire can change into each other, but there's nothing strange about that. That happens in a purely straightforward and natural manner. But Aristotle would say all things in the terrestrial realm are made up of earth, water, air, and fire, some combination of those, and behind those lay the 2 principles of cold, wet, hot, and dry. Now, what Aristotle thinks of as elements here are probably more akin to what we would think of in the modern world as phases. So earths are effectively solids, waters are liquids, airs are gases, and fire is fires. That doesn't quite match up, but you get the general drift of what's going on there. As Professor Roos said, Aristotle has an idea of natural motion. Very important here, Aristotle has no conception of gravity. He knows that if you throw something in the air, it will fall down and all the rest of it, but he does not explain that in terms of gravity, nor does he explain the motion of the planets in terms of gravity. So Earth is held to be heavy and has a natural place at the centre of the universe. Right? So Aristotle's cosmos is an absolute one, and that centre of that cosmos is a physically important place in the sense that Earth moves straight down to the centre of the universe. Water is less heavy. It too moves straight down to the centre of the universe. That's its natural place. But then if we think cosmologically, you've got the Earth as a rough sphere surrounded by water fitting into all the hollows. Okay? Now, now important. Air is positively light. It is not heavy, it is positively light. By that means, Aristotle means that it does not move towards the centre, it moves towards the extremes of the terrestrial realm. And again, it moves in a straight line when it's moving naturally. Fire is held to be lightest, and its natural place is at the edge of the terrestrial realm. Right? So you get this sort of onion effect in Aristotle. In the centre, you've got Earth, surrounded by water, surrounded by air, surrounded by fire. They each have their natural motions, and if they are unimpeded, and I have found a nice prop, something that isn't going to damage the lecture theatre or any of the students. So this is metal. So metals for Aristotle are mostly earth, but with a bit of water there as well. Why? Because metals ultimately will melt. Right? So they are solids, so they're mostly earth, but they must have a principle of fluidity in them as well. Right? So stones have less earth. So at the moment, I'm stopping this from executing its natural motion. Off it goes, and I stop it again. Right? For Aristotle, no forces are required for something to execute its natural motion. Forces are only required to stop it from doing its natural motion. And this is the bit where I have to make sure I don't damage any students. There are also N-force motion. That's an N-force motion which will gradually die out for Aristotle because it's not natural in a straight line. There is also a fifth element for Aristotle known as the ether or quintessence. That goes round in circles, that's its circular motion, and that is what is natural to it. Let me take you to a diagram of Aristotle's cosmos. Earth in the middle, earth, water, air, fire, up to the realm of the moon, outwards to the celestial realm, out to the fixed stars. Professor Bruce has always already described some of this, so I won't say a lot of it again. Interestingly for Aristotle, he thinks that mathematics applies precisely to the heavenly realm, but not so to the terrestrial realm. I'll just give a couple of reasons for that. Imagine a geometrically perfect sphere on a geometrically perfect plane. How many points does the geometrically perfect sphere touch the geometrically perfect plane? One. Excellent. Good. Now, imagine a football on a field. At how many points does a football touch the field? And the answer is lots. So says Aristotle, the abstractions of pure mathematics are not applicable to the real world. Right? So Aristotle says mathematics are not important. Again, the key figure here is Galileo, who in many ways introduces applied mathematics, and that's what Aristotle is lacking. Aristotle thinks the world is made up of qualities, which I'll come to in a moment, and he thinks those are difficult to quantify, and he tends to think in terms of, what's that colour? White. White, whiter, whitest, hard, harder, hardest, rather than in terms of quantities. There is also this. Imagine you have two comedians and each tells you a joke. Is it proper to say that one of those jokes is 1.8654327 times as funny as the other joke? No? What excellent Aristotelians you are! Because Aristotle would want to say funny, funnier, funniest in relation to jokes. Right? Now, you've got the point about jokes. Aristotle applies that to the rest of the world. He thinks that the rest of the world should be described in that manner rather than in precise quantitative terms. Aristotle and explanation. Aristotle thinks that everything has a potential which it will actualize. So an acorn will grow into a tree and it has the potential to do so unless something stops it from doing so. So everything will seek to actualize its potential. Now note that that is fundamentally a biological paradigm or allegory for explanation. Aristotle will use biological modes of explanation within physics, right? So when we have this piece of Earth, if I let it go, it will actualize its potential to move towards the center of the Earth, right? So Aristotle, instead of explaining biology in terms of physics, tends to explain physics in terms of biological explanations. That's quite widespread in the ancient world, but again, that's going to dissociate him from Leucippus and Democritus quite strongly. What Aristotle would say is that all objects have a natural place, they're going to go there unless stopped. Earth has potential to be at the center of the universe, all objects fall unless prevented. And fire has the potential to be at the periphery of the terrestrial realm. Ether has the potential to keep on moving, and it will keep on moving in circles, and it actualizes that potential. For Aristotle, there's a sense in which the heavens are more actual than the terrestrial realm because the ether is always actualizing its potential. Why is there a fifth element for Aristotle? Because he recognizes earth, water, air, and fire are always changing, but he thinks in the heavens there is no change. Therefore, they must be made up of a different element. He recognizes, yes, okay, sun, moon, 5 planets all move relative to the fixed stars, but he knows from the Babylonian records that they move in cycles. So there's no overall change in these things. So he wants to say there's a fifth element there which doesn't change at all. How would we explain a tree? Well, we would go botany, biology, biochemistry, chemistry, physics, would we not? But that is to assert a specific direction of explanation. That is to explain from the biological to the physical, and also to assert a reductive type of explanation, which is to say that we can explain the biological level at the biochemical level, and you can explain that in turn at the chemical level. Aristotle would reject that mode of explanation and say that we must explain this biologically and holistically. Last thing to hit you with, I think, qualitative metaphysics. Aristotle believed that, sorry, let me rephrase that. If you give the atomists a catalogue of, tell the atomists to give you a catalogue of what makes up the world, they would say atoms and void. If you ask Aristotle, he would say the world is made up of qualities. So what is this? It is whiteness, it is flatness, it is impenetrability, it is coldness. And that is what is there for Aristotle. Right? Aristotle did not believe that the world came apart into atoms. He thinks that these qualities are real. So Aristotle is, in effect, a WYSIWYG philosopher. What you see is what you get. Right? You see these, they are there, and that's what causes you to see them, because they really are there. Aristotle also thinks that behind all this is something called prime matter. So if you think of an object, this one will do, careful Andy, these break. What happens if you take all the qualities away from that? That hasn't got many qualities, let me have something else. Whee. Take away whiteness, roundness, plasticiness, and all the other qualities from this, and what have you got left? And I don't expect a definite answer to that, because this is a philosophical conundrum that's gone on from Aristotle's time. Some people say nothing, this is just its qualities. Aristotle would say, no, there is something left, and that is prime matter, something that is just matter without any qualities. Aristotle doesn't think that prime matter actually exists, only exists potentially, because he thinks that whereas you might think of a different shape for this thing, you can't think of it without shape, right? But he thinks there is prime matter there. So for Aristotle, the world up is made of prime matter with these qualities. That means the world is a plenum, it's densely packed, and Aristotle thinks there can be no vacuum. Why does he think there's no vacuum? Rate of motion for Aristotle is proportional to the resistance of a medium. Take the medium away, so you've got a nice big zero on one side of your proportionality relation, and that means the other side must be infinite. Things cannot move at infinite speed. That is inconceivable, and we do not see that in nature. Therefore, there is no vacuum. End of debate. No vacuum for Aristotle. So he thinks that what Leucippus and Democritus are up to is inconceivable and totally mistaken, because he thinks their atoms would start to move at an infinite speed, and that simply can't happen. There has to be some resistance put up by the medium. This bit I've already done. This is about quantification, so I'll finish by just summing up this feud between Aristotle and Democritus. Aristotle says, no atoms, no void. Right? Qualitative metaphysics and prime matter and a plenum. Qualities are fundamental for Aristotle, and Aristotle will not allow a reduction in qualities. Qualities are real, they're actually out there. There really is whiteness here, there really is hardness and all the rest of it. Leucippus and Democritus would say things roughly like we would say in the modern world, only not quite so sophisticated. Why do we see that as red? Because it gives off light of a certain wavelength, and our brain sort of interprets that as red. Is it actually red? Are the atoms that make that up actually red? No. So the quality of redness we reduce down to something else. But Aristotle would say, no, qualities are real, and I'm not going to have them reduced. Aristotle would also say matter has potential, it can actualize, it is not inert, it is not just dead matter, it is something that matter can do. Aristotle would also say the physical needs to be explained biologically, not the biological explained in terms of the physical. Aristotle would also say there is one and only one cosmos. It has no beginning and it has no end. Right? And we can treat it as if it has been designed. So there's a difference of opinion between Aristotle and Plato here. Plato thinks there's order in the world because it has been imposed externally by some craftsman god on chaos. Aristotle thinks that that order is inherent in the world and it's always been there and always will be there. So there's only one cosmos and there can only be one cosmos for Aristotle. And again, he would be very much object to the view of Leucippus and Democritus on this, because he thinks that cosmos has an inherent order to it. So the ancients, just like every other period of time, had feuding physicists, and they feuded on this issue of matter. It starts with Parmenides and his slightly odd views. It starts with a reaction to Parmenides by Leucippus and Democritus in saying, nope, we're going to have atoms and an empty void. You have Plato having something to say about that in terms of beauty and mathematics and order, and then you have Aristotle saying, you're completely wrong, Leucippus and Democritus, there aren't atoms and there's a whole different way of looking at things. I think that's about it. Thank you.
Thanks very much, Professor Gregory. We do have now a few minutes for questions, and I shall start with the gentleman here in a blue shirt.
Great, thank you very much. A brilliant talk, and I just thought it's not a question, it's a comment, but just to connect Plato with where we're sitting. Modern string theory posits that we're all basically made of strings and brains, which would correspond almost exactly to Plato's planes. So bearing in mind there are now most probably a score of mathematicians here studying string theory, and tens of thousands across the world, it basically shows we've come full circle to Plato's thinking.
Yes, thank you. I think one has to throw a bunch of caveats around that, of course, because ancient and modern, being cautious about lots of things. But I think fundamentally there is a line of thought which is given its first airing with Plato about beauty, about mathematical simplicity. Now, if I remember my modern particle physics, it all runs off something called Lie groups, which determine how many particles you got. So when you've got the cyclotron at CERN, you don't go click, oh, what's in there? Firstly, you go to the mathematics and work out the mathematical characteristics of something, and only then do you look for it. I think that's a very Platonic thing to do. If you ask me, there's the score between Plato and his opponents is actually 1-1 with 1 to go, right? Because I think Plato wins on this question of matter. I think on the issue of evolution, Plato is wrong, because Darwinian evolution does work by a multiplicity of accidents. On the issue of one cosmos or multiple universes, I think the jury is still out. I think we are still on that question, and I believe physicists are trying to devise experiments to test whether there are multiple universes. I think that actually misses the point about multiple universes myself, but that's a different issue entirely.
The theme of Feuds, there's a vast number of physicists who think string theory is, in famous words, not even wrong.
Yes.
That's great. So, next question is from the lady in the red jumper here.
Thank you for a superb talk. Was Aristotle an atheist, or did he consider that to be a completely different entity?
Aristotle is a theist, and what his God does is thinks about thinking. So what is the best thing that Aristotle thinks that can happen? That is thinking. You can see Aristotle's a bit of a philosopher here, right? So what would be better than thinking? Well, it must be thinking about thinking. But Aristotle's God does play an important part in Aristotle's cosmology as well, because if you ask, why are the heavens moving round in this circular motion, it is for the sake of the prime mover, who is Aristotle's God. So there's never a position where Aristotle has to say, I'm beginning the cosmos, I've got to give it a push to get everything going. That's not how Aristotle thinks about things. He thinks that the heavens have this natural motion which they execute for the sake of the prime mover. And I appreciate that's a strange way of looking at things, but Aristotle has different ways of explaining things. Thank you.
Great. I was aware of a question somebody, yes, gentleman, yes, in the maroon, yeah. Sorry.
Thank you so much for the talk. I've got two questions. The first would be, did the idea of the ether precede Aristotle in the sense that you have 5 Platonic solids, but Plato only had 4 elements? So did he ever relate the 5th Platonic solid to the ether? And the second question would be, if you had some prime matter, if you drop it, will it drop to the ground, or will it go up?
I'll answer the second question first. If you had some prime matter, if you genuinely had some prime matter, right, which you can't have according to Aristotle, I think the answer is it wouldn't move at all, because it doesn't have any characteristics. You have to add in the qualities before it would have natural motion. So if you gave it the qualities of Earth, then it would have natural motion downwards. If you gave it the qualities of ether, then it would move in a circular motion. I didn't catch the first part of your question. Could you give me that again?
So the idea of the ether was, as I gather, it was from Aristotle, but Plato, there are 5 Platonic solids,
yeah,
but only 4 elements.
Oh, yeah.
Plato. So I was curious whether the ether was the 5th Platonic solid.
So, yes, you have the issue of the dodecahedron, right? Plato's a little bit quiet about this. There's a certain beauty to the other four. What Plato says is it's somehow tied up with the cosmos. And I think probably the answer to that is that if you look at a dodecahedron from certain aspects, it has got 12 points to it, and that points to 12 houses of the zodiac. That needn't be interpreted astrologically, that's just a way of mapping the heavens. Sometimes you see, anachronistically and entirely wrongly, that the dodecahedron is associated with ether. And when I was getting the overheads for this off of Google's image, there were lots of them which associate the dodecahedron with ether, but that's actually not in Plato. He just says it's tied up with the cosmos somehow.
Good. So, gentleman here was next.
Thank you for a fascinating talk. I was about to ask two questions if I could. Fortunately, my first one has just been answered. My second question was that for Plato, you say the cosmos is designed.
Yes.
There's some sort of best design. Did he have any suggestions as to who or what was the designer?
Yes. In ancient Greek, he's called the demiurge. And demiurge literally translates as skilled workman. Right? Now, that's a very interesting thing for Plato to say in itself in the history of Greek theology, because you wouldn't get anything like that in Homer or Hesiod or any of the previous philosophers. This craftsman god clearly is also well up on his mathematics and geometry, because he crafts the world mathematically in geometry. The first thing that Plato says is that those triangles and the atomic shapes, is he marks them out by means of shapes and forms. Can we say a lot more about this craftsman god for Plato? It's difficult to do so with any great certainty. I think the key thing for Plato is something like this. How is it that we as humans can get some sort of grip on the world? How do we say that this explanation is better than that one? If we assume a God has made everything for the best, then, and has made that mathematically, geometrically, and all the rest of it for the best, then if we make our explanations the best mathematical and geometrical explanations we can, then they will match up to what's actually out there. So I think that God plays an important cosmogonic role. It also plays an important epistemological role for Plato. I'm afraid I can't say a lot more about Plato's God, because Plato doesn't personify this God. He just says that this God has got a perfectly good will, and that means that the world has been made in the best possible way and will persist forever, because it'd be a wrong thing for a person with a good will to dissolve the cosmos.
So the role of the demiurge is to decide what is best?
Yes. Yeah.
As our last question, I'm going to take the gentleman in the penultimate row, pink, red shirt.
How did Plato decide which shape assigned to which element?
That is a very good question, to which I would be delighted to have a lot more information from Plato. The cube he held to be the most solid and persisting of these shapes, and he thought the most solid and persisting of the elements was Earth. Right? He thought that the tetrahedron, because it was the smallest and it had the sharpest faces, was most likely to be associated with with fire, because fire cuts things up. Right? So that's why the tetrahedron is fire, because it moves quickly and it's got sharp angles, cuts things up. Why the others are water and air, I think that may be lost in the mists of time. Right? But Plato has this sort of loose association like that. One of the great criticisms of it is how empirical is this theory, and the answer is it's not. Right? And that's no great surprise with Plato, because he's into the beauty of it. But I mean, that's about as far as we can go with it. Tetrahedron is fire because it's small and cuts things up. Earth is, because Earth looks solid and square, the cube looks solid and square, it's associated with Earth.
Thank you very much indeed. I think we ought to thank our speakers.
Thank you.
Without further ado, I'm delighted to welcome our third speaker this morning, Professor Rob Iliff from this very university, and he's going to talk to us about Newton and people he didn't like.
Yeah, I will talk about Hooke and Leibniz and try and come to terms with some ways of thinking about why Newton had problems with these individuals above others. I mean, there's a third person with whom he had problems, John Flamsteed, but that's not quite at the same level, I think, of the existential problems that Hooke and Leibniz played in his life. So just some background to Newton. He was, depending on which part of the world you're in, he was born on the 25th of December, 1642. So that's in England. He's born in the same year that Galileo died. Paradoxically, in the place where Galileo died, Newton died on the 4th of January, 1643. Just a few months after the Civil War began in England, Newton's father died in October 1642. We don't know very much about that. And his mother remarried when he was very young, producing 3 half-siblings for the young Isaac. We know that Newton spent a lot of his time. We have good evidence about what Newton did as a young man from Newton and, in fact, from other people. We know that he went into local fields and did what's called simpling, looking for medicinal plants. He was interested in astronomy. He was interested in building dolls' houses, kites, clocks, sundials, and so on and so forth, playing philosophically, as the antiquarian and friend of Newton, William Stukeley, put it in the 1720s. Although he had other distractions and, according to Newton himself, didn't do very well at school, occasionally he always had the ability to pull himself back and outpace his colleagues. And he went to Trinity College in 1661 in the summer, just after the restoration of Charles II. And Trinity College moved from and I think this does matter for Newton, whether it matters for this story is probably for you to decide, but Trinity College went from a very Puritan establishment back to a very conservative, reactionary Church of England establishment. And these, I think, clearly have influences on Newton, who is a devout, godly boy. This is a picture of Woolsthorpe Manor in Lincolnshire, near Grantham, from the first decade of the 19th century, with a barn stuck on the side. And this is where Newton grew up. He grew up in a place where he had a lot of servants. He's not a poor boy made good. He comes from a very wealthy family. His mother was one of the wealthiest people in that part of England. But nevertheless, Newton has this shtick, or this business of independence that marks him out through his life. This is from a book that he read, The Mysteries of Art and Nature by Jonathan Bate, 1656. We know that he built this clepsydra, a water clock, and this was the source of his ingenuity when he was a boy. Newton at Cambridge studied the basic curriculum, not a billion miles away from the one that Andy discussed, Aristotle and to a lesser extent Plato, until early 1664, when we know, because it's lavishly documented in materials that are at Cambridge University Library, he started to read the latest works in mathematics, particularly by John Wallis and others, and he read the latest works in natural philosophy, the works of people who were at the newly founded Royal Society, particularly Robert Boyle and, as we shall see, Robert Hooke, and he studied these things in an ultra-critical way. He immersed himself in these works, he imbibed the doctrines, and he wrote against them, and devised experimental programs to test his own new ways of thinking. And there isn't really anyone who's doing this kind of thing. I mean, he could have been doing it and not been doing brilliant work, but he did it, and he did pioneering brilliant work in 3 separate fields: mechanics, mathematics, and optics. We know that in 1665 to 6, he found what later became called the fundamental theorems or algorithms of calculus, differential and integral calculus. the binomial theorem. He did stupendous work, I think, in mechanics, and he discovered the heterogeneity of white light, which is that primary white light that comes from the sun is composed of more basic primary colored rays. And that overturned a theory that had been held by virtually everybody for 2,000 years, which is that colors are produced when white light is modified in its passage to another medium. Newton, as you will have guessed, argued that when white light, for example, hits a prism, the colors into which it will be broken down going through a prism are already constitutive of the white light before it hits the prism. For his work in optics and predominantly mathematics, Newton was made the second Lucasian professor of mathematics in September 1669. This is the famous attempt by Newton. This tells you what Newton is like. This is the calculation to 55 decimal places of the area under a hyperbola. This is the only image of the crucial experiment, with light coming in from the right, hitting a lens, then being put into a prism, and then going through a board on the left, and an individual primary ray being separated, and then that being further refracted through a prism on the other side of the board. And what Newton wants to say is that the defining characteristic of a ray of light is its index of refraction, or what he calls its degree of refrangibility. And that's an extraordinary thing to say. I mean, he will move as a mathematicist, natural philosopher, to say that the defining characteristic of a ray of light is not that it is composed of atoms that spin or travel at a certain speed, although he does believe that in private. But in public, he will say it is its index of refraction that marks its obstinate capacity to retain its degree of refrangibility through successive refractions that is the characteristic of a primary coloured ray. The first paper Newton published was in February 1672. It received serious attention, criticism from Christian Huygens and Robert Hooke. Hooke in particular was upset by a throwaway line Newton had given in the paper, saying that nobody in their right mind could doubt that light was particulate, which he shouldn't have said, and he regretted doing that. But the key point of the paper is to put forward a mathematicist view of what a ray of light is. As it were, like most mathematicists or mathematicians who go into natural philosophy, the price of the benefit of mathematizing natural philosophy is that you hollow it out. You are no longer able to talk about what the stuff of light is, because you are moving towards defining light or anything else mathematically. Hooke made it known that he thought that Newton's work was merely a hypothesis, a theory, and Newton took umbrage at this. He became very angry, and in a number of letters he wrote in 1672-73, he argued that his work was more than a hypothesis. It was mathematically absolutely certain. This is what this guy's like. What he's done is certain. It doesn't have the characteristic of something that is less than that degree of mathematical certainty. It's certainly not an hypothesis, as he says. Whereas Robert Hooke's stuff is a hypothesis. Robert Hooke's defense of a wave theory of light for Newton is the defense of something that cannot be made absolutely certain, and therefore Hooke should not defend it or be committed to it in the same way that Newton is committed to his own ideas. And this exchange with Hooke marked out Newton's dislike or hatred for the public sphere, I think, for the rest of his career. Newton will always think that the best way to do science is to do it in private, before a group of like-minded, smart people who agree with everything he says. And that's conversely, the public sphere is a place for where the vulgar misunderstand that which they have no hope of comprehending. That's Christian Huygens. That is relevant. This book appeared in January 1665 from Robert Hooke, and it's a book that Newton devoured very quickly. in the mid 1670s, Newton had withdrawn from the public sphere. He'd been used by the editor of the Philosophical Transactions, Henry Oldenburg, as a way of filling up the space of the Transactions with debates about Newton's theory. And Newton retreated back to Cambridge sort of physically and mentally and devoted himself to alchemy and theology. But like Al Pacino in Godfather 3, he kept on being pulled back in to debates about the nature of light, because people care about it. And at the end of 1675, he unwisely gave a talk which he called the Hypothesis on Light and Colours. He provided a paper, anyway, that was read out to the Royal Society. It's an extraordinary insight into his own personal natural philosophy. It's a rich account of how music and light and colour and everything else are all kind of connected in some extraordinary way. Hooke heard this and accused Newton of plagiarising from Micrographia. And with Christopher Wren and others, he started a new rival group right at the end of 1675 to degrade the quality of the Royal Society. And this is a deliberate attempt by Robert Hooke to destroy the Royal Society by creating a new society. And the very first thing they discuss in their first meeting is how Newton has plagiarized from Micrographia. So Newton gets to hear about this, and he took umbrage, that is to say, he went ballistic, being accused of being a plagiarist. And there's some wonderful material in his private writings about how it's Hooke himself who is a plagiarist from Descartes. And this is where you really see Newton being brilliant, I think, is where he gets angry. I mean, people shouldn't make him angry, like the Incredible Hulk, because when he gets angry, people wouldn't like him. And he destroys Hooke over the next few years. But he does write this famous letter in early February 1676, where he says, in the wake of that, if I have seen further than you, and I have, it's because I'm standing on the shoulders of giants. And he never forgot what Hooke said. Right to the end of his life, he remembered that slight by Hooke. The third and greatest contest between Newton and Hooke concerned the allocation of credit for key doctrines of the Principia, which was published in the summer of 1687. In a series of brilliant letters written in 1679-80, Hooke, who was now Secretary of the Royal Society, had tried to drag Newton back into discussions about natural philosophy. And he'd asked Newton what Newton thought about producing an elliptical orbit by compounding inertial motion with centrally attracting forces in planetary objects. And Newton responded. Again, it's a long story, but essentially he took on board a lot of what Robert Hooke said, that the general approach that Hooke provided for him is found in the Principia. It provides the basis for Newton's analysis in Principia Mathematica, although, of course, Newton goes way beyond anything Hooke could possibly have done or imagined. When it was known in 1686 that this transformational book was forthcoming, Hooke asked people to tell Newton that he expected some credit for the core doctrines in his book. And Newton told him, again, remotely, to go forth and multiply. And again, there's some wonderful discussions that we know took place in coffee houses in 1686, where Hooke said, essentially, he'd had this proof that Newton was going to give in the Principia, but Hooke had kept it to himself, knowing how important it was. And his friends broke with Hooke, saying, if it had been that important to you, you should have published it. And it's a very interesting debate where Hooke breaks from people he'd been close to for over 3 decades. Newton understood in this action that Hooke was turning philosophy into a law court, and I think that's very important for Newton. Newton hates the idea that natural philosophy is simply about disputing. He hates the idea that natural philosophy is about metaphysics. He hates the idea that natural philosophy is about the value that's given to something by people who read books and act as sort of witnesses and warrantors for what the book describes. For Newton, what you put forward as a natural philosopher is intrinsically convincing, or it isn't. If it's attached to mathematics, like his work in Light, or if it's attached to mathematics, if it has a mathematical basis, as in Principia Mathematica, with the law of universal gravitation, then you don't need thousands or tens of thousands of unworthy people to say that they warrant it or believe it's true. It simply is true. It helps if you've got experts, the 2 or 3 people, other people in the world who understand the Principia. It helps if they say it's kosher, but you don't need them. And so Newton's problem, I think, is the introduction of legalistic behavior and discourse into the realm of natural philosophy. And he complains in a wonderful phrase about Robert Hooke turning philosophy, that is science, into a litigious lady. And it's only the great diplomatic work of Edmund Halley that pulls Newton back in to finishing the Principia. When the Principia was published, Newton very quickly became a star. He was the first scientific celebrity. People came to see him. They came from Italy, they came from Russia to see Newton. He became an MP in the Glorious Revolution of 1689. This is a picture from 1689. It's the earliest one we have, by Godfrey Kneller. Throughout the 1690s, he became a government official. He was Warden of the Mint, then Master of the Mint from 1696. He became President of the Royal Society in 1703, and he was knighted for his services to government in 1705. The Queen Anne took a break from horse racing at Newmarket to come down and tap him on the shoulder, and then went back to the horse racing. I did mean to try and find out what the races were that day, but I never got around to it. This is also Kneller now. This is 11 years later in 1702, just as Newton is becoming a majorly powerful figure in natural philosophy and in the English, soon to be British government. And then we have Leibniz. Leibniz, it's hard to describe Leibniz's brilliance, least as great as Newton. Extraordinary breadth that Leibniz has. He's a diplomat, he's a mathematician, he's a librarian. His key job is as a librarian, or at least it's supposed to be, a librarian writing the history of the House of Brunswick. But it's his mathematical brilliance, produced really while working with Christian Huygens in Paris in the mid-1670s, that sees him develop what we now take to be the modern notation of calculus in 1675 to 6, and resulted in him publishing the first articulation of calculus in 1684 and 1686. It's those publications that forced Newton to publish the famous fluxions lemma, which is just inserted in at the last moment into the Principia Mathematica. It's the only part of the Principia where you see Newton's expertise in calculus. As time went on, Newton had lackeys, a number of people whom he did nothing to control, who went from saying that Newton had some entitlement to the claim of the inventor of calculus, to saying that Leibniz's calculus was inferior, and also that Leibniz was a plagiarist, having somehow seen Newton's private writings on mathematics, which Newton had, of course, done these things in 65 to 66, but because of his distaste for the public sphere, he had not released them to more than a handful of people. As Leibniz became more interested in, and Leibniz is a brilliant, accomplished metaphysician, as Leibniz became more interested in Newton's science, he became more worried by what he saw. And in a way that, again, there's been much pen, much ink has been spilled over writing about this, But from 1710, 1711, Leibniz, who was a member of the Royal Society with Newton as president, Leibniz demanded of the Royal Society that the Royal Society not back those people who had said that he was a plagiarist. And of course, under the heading of Newton, the Royal Society refused to do that. Newton refused to rein in his followers. As Leibniz looked more closely at Newton's doctrines, he saw something terrible. He saw something diabolic. Newton's notion of absolute space was absurd. His notion of a sensorium, which is to say that God had a peculiar relationship with his creation, as if Leibniz said it, Newton had said it was the organ of God's sensing, which is a heresy in any branch of Christian philosophy. The more he looked at what Newton had done, the more disgusted he became. When he looked at universal gravitation, he saw something completely absurd. You know, the idea that two objects on either side of an infinite space could influence each other in real time was absurd. No one, not even the medievals, had ventured to claim something so stupid, dangerous, and absurd. And Leibniz is one of a number of top people in Europe. The biggest players in European natural philosophy. They admire the accomplishment of the Principia Mathematica, but its core doctrine, universal gravitation, is absurd. You know, Newton has, in a sense, hollowed out the world. Newton doesn't talk about the physical stuff of the world. He can't offer a material physical cause of universal gravitation. And so he's engaged, as far as most people are concerned, in a dereliction of scientific duty, which holds that the duty of science, the point of science, is precisely to explain phenomena in terms of their physical underpinnings. And you see, again, that connection with what he did to the ray of light. He hollowed out the ray of light in 1672, and now he's hollowed out the entire infinitely large universe. That there is, you know, as if you think back to what Andy was saying just now, you know, for Newton, all of the matter, and he says this, all of the matter in the infinitely large universe could be put in a peanut shell, because nearly everything is empty. The entire universe, all of you here, are basically empty. There's nothing there, according to Newton, or is there? These are the kind of things that Leibniz doesn't like. There he is. In response to criticisms from Leibniz, Newton produced a third rule of philosophizing in the second edition of Principia in 1713. This is an extremely important rule. It's his defense of induction, which is quite interesting. We can talk about that later. But he's moved from a sort of ultra-mathematicist kind of natural philosophy to one which is slightly more inductivist. The rule of philosophizing is about what's required to corroborate claims that you make inductively. And it was explicitly directed against Leibniz, and it contained the statement, again anti-Leibnizian, we are certainly not to relinquish the evidence of experiments for the sake of dreams and vain fictions of our own devising. I mean, Newton is now countering Leibniz's claim that the Newtonian philosophy is a fiction by now saying the entire Leibnizian philosophy is a fiction. And Newton defends with increasing virulence the idea that he himself does not feign hypotheses. And hypotheses non fingo becomes the cri de coeur of the Enlightenment. You know, we do not make hypotheses. What we do is based on mathematical certainty, empirical evidence, and hard work. That phrase comes from the second edition of Principia. And it's part of his attack on Leibnizian vortices and hypotheses in general. And I think in the last 3 years of Leibniz's life, he died in November 1716, we see this extraordinary battle, which I think is endemic within the way Newton thinks anyway, but a battle between these two giants of the period about which one was pure fiction and which one was the truth. Months before the second edition appeared, in the summer of 1713, Newton had published the Commercium Epistolicum, a text-based documentary effort to show that he had developed fundamentals of calculus half a century earlier. So this is just a publication of letters and his own documents that proved that his work preceded Leibniz's in priority. And again, this is something I want to point to at the end. This is Newton's own propensity for litigation. That this is where he goes. Whenever proof is required, he displays himself to be, first of all, a brilliant documentarist, but also, I think, a conspiracy theorist of an extraordinary ability. This very substantial text, the Commerce of Letters, didn't convince Leibniz's followers. You have to understand that by this time, Leibniz's followers include Johann Bernoulli, Jakob Bernoulli, Daniel Bernoulli, Jakob Hermann, Leonhard Euler is just about round the corner. They have gone far beyond what Leibniz's followers have done by using Leibnizian notation and Leibnizian techniques. All of that is happening while this debate is going on, but Newton is focused on proving his own priority. Leibniz increasingly objected to Newton's documentarist approach and gradually came to see Newton as a kind of diabolical puppet master who incited his toadies to act in his defense, conniving in their actions. And there Leibniz is in a strong position until Queen Anne died on the 1st of August, 1714, because Leibniz's own tutor and patron, his patron, Georg Ludwig, became George I of England and comes over to England soon after he's made king. And with him he brings his niece, Princess Caroline, married to Georg's son, who will become George II in 1727. And Princess Caroline is a tutee of Leibniz. She is his favorite student. And she's going over into the heart of the enemy. And within days of her arriving, Newton and Samuel Clarke, Newton's lieutenant, are going round to her house, Kensington Palace, and they are saying, would you like to see some experiments on the void, and so on and so forth. We call it intellectual grooming. There's Newton at this time. Leibniz began a correspondence with Samuel Clarke, the most famous philosophical scientific correspondence of the 18th century, from 1715 to 16. And in the fourth letter, we see this big change in Leibniz's view. He becomes much more concerned, I think, about what he sees as underpinning this is what he knows to be the loss of his student to the enemy. But he becomes, I think he writes brilliantly about the dangers of the Newtonian philosophy. And his letters are full of the idea that Newtonianism is a fiction and a chimera, or rather a bundle of these things. In a codicil to a letter intended only for Caroline, Leibniz told her that he believed in the void, so this is a key Newtonian doctrine. He believed in the void when he was a kid, when he was a young man and not fully formed. It was a pleasing imagination, but the product of my own ignorance. Men imagined nature was as finite as their own mind, so atomists believed that nature was finite because they themselves are finite creatures, Leibniz said, but wrongly. The least corpuscle is actually subdivided in infinitum and contains a world of other creatures, which would be lacking if that corpuscle was an atom. To assert that the subdivision of nature stopped at the size of an atom was an arbitrary fiction, humans conceiving the world in their own image, which is exactly the claim Newton makes about his own enemies. At the bottom, you can see that Caroline received this letter on the 7th of May, 1716, and the next day she passed it on to Newton. That's Newton's writing at the bottom. So she's in the enemy camp. She's passing these private letters straight on to the head of the enemy. In the final letter that Leibniz wrote, he claimed that Newtonians peddled a superficial philosophy that forged things such as vacuous spaces and atoms. But his superior reasons, the superior reasons of metaphysics, did not allow them. The Newtonians' collective strange imagination made all matter gravitate to every other piece of matter. But what filled up empty Newtonian space? Was it full of spirits, like the sort of odd imaginations of the voodoo-wielding medievals? People were once again returning to the spectres of the imagination, he said, and to the perpetual miracle, or occult quality, or chimera of universal attraction, and ultimately to the kingdom of darkness, which is, of course, is the Christian reference to the realm of the devil. And he means that. He thinks Newton's stuff is diabolical. While Leibniz adored really good novels, like the science fiction written by Christian Huygens, irrational chimeras were becoming fashionable again in England. He said, no one would have published this rubbish in the early years of Charles II, i.e. before Newton came along. Oblivious to his own cultivation of acolytes, Newton claimed that Leibniz had created an army of disciples who were trying to dominate the Republic of Letters and populate it with his conceptual excrescences. Leibniz, at the end of his life, came to see Newton's doctrines as lying at the heart of a diabolical national cult with Newton as its head. Newtonianism, he said, was a false religion that had acquired illegitimate power through its proximity to the new sovereign. Newton's toadies did his bidding, and its core doctrines were a matrix of incoherent fictions. This is Newton's response, because we don't have time, but at the top, I don't know if you can see at the top there, it reads, Leibniz, and there's hundreds of these kinds of things in Newton's writings. This is all available online, Cambridge University Digital Library. You can search it through the Newton Project. This is Newton's id. This is what he thinks. Leibniz commends experimental philosophy, but adds that when experiments are wanting, it is allowed to imagine hypotheses and expect that until new experiments shall determine which of them are true. And upon this account, he thinks his philosophy may be justified, but he should consider that hypotheses are nothing more than imaginations, conjectures, and suspicions. And that is Newton's response. We can see that this is a battleground of accusations of fiction and romances. And by the way, Newton does not like romances or fictions. He hates fiction. He's got no serious books on fiction were found in his library. He's scared of them. He's scared of them. Right, the last two pages. Historians, we want to understand why Newton did what he did, and ultimately, obviously, we think this is partly due to Newton himself. It's his view of the world, the way he was brought up, his own psychopathologies. But historians rightly find psychologizing or appeals to psychology unhelpful, or they fall short of what's required in terms of an explanation. And they try and look at how individuals are shaped by and interact with their context. What structured Newton's or governed Newton's attitude to Feuds? Partly these are mental structures and partly social structures. And the latter, of course, the social structures that surround Newton are not static. Newton himself is influencing those structures. He gets power. He gets the authority to transform the world in his image. Newton professed deep hostility to metaphysics, to the public sphere, and to disputes about intellectual property. He keeps telling people he hates disputes. These brought disgrace and legal discourse into philosophy. It turned philosophy into a litigious lady. And Newton's always key that natural philosophy is not a forensic space. It's not about rhetoric. It's not about how clever you are and how well you argue. It's about the truth. Yet Newton's own actions, I think this is key. Newton writes about feuding all the time. He's deeply concerned about feuding. Newton's own actions were, I think, made inevitable the very kinds of feuds that he himself professed to despise. For example, keeping his work private. I mean, how else is one going to show that one has priority? How else is one going to influence the public sphere unless you publish things? But Newton has a very, very different, elite aristocratic way of thinking about the significance of his own work. And I think also as a basis for this, and we see this in the battles over romances and fictions, Newton is deeply hostile to fiction. It is undoubtedly related to what we know to be a kind of Calvinist element in his own religious thinking. He's a deeply devout religious man. In Calvinism, the godly are told that the mind is a dungeon. The hand makes what the mind conceives, and you get idolatry because human beings are hardwired to mistake the products of their own minds and hands for what really exists outside in the real world, the products, what is divine creation. That is who we are within Calvinism. We're sunken, fallen, depraved creatures who always mistake our own hypotheses and theories and productions for what's really the case. His anti-hypotheticalism, which underpins his critiques of Hooke and Leibniz, is closely related to his attacks and I think his fear of the power of the imagination in human beings in private. This personal attitude shows itself in a broader cultural form. In his attacks on hypotheses non fingo, I, Isaac Newton, do not feign hypotheses. I'm not prey to mistake the products of my own mind for what's really out there. That's what that means. In a more sort of grander sociological, social form, Newton transformed the world around him into a space where he could perhaps counter the work, the machinations of people like Hooke and Leibniz, who created armies of disciples to invade his own territory. In these battles, Newton had to marshal powerful groups, like his friend Lord Halifax, the Chancellor of the Exchequer, who made him the head of the Mint, like the King, who personally vouched for Newtonianism, like Princess Caroline. All these people are enrolled as allies into Newton's world, and they are a necessary condition for Newton triumphing, as he did briefly. Newton had to enroll these allies and did so. Thank you.
Thank you very much indeed. So as the first question, the first person I saw actually was a gentleman in the penultimate row, red shirt.
Hi, a couple of questions about Hooke. You said he accused Newton of plagiarism for micrographia. What was that specifically? And also his rival society to the Royal Society, how many people joined that? What happened with it? Because he then went back to the Royal Society, obviously.
Yeah, I mean, the answer to the first one is a complex one. It is complicated, but essentially there are, basic claims about the way nature is. I can't go into any more detail than that because it would take a couple of hours. The issue between them, I think, is very interesting, which is, if you look at Newton's response to it, it is about whether they're similar or dissimilar. So that the rhetorical form of argument is that in order to show plagiarism, you have to show that someone's work is similar to your own, or not dissimilar. And so most of the intellectual work that Newton is doing is to show, first of all, that Hooke's work is very different from his own, and then to show that Hooke's work is very similar to Descartes, because he wants to show that Hooke is a plagiarist, and he wants to show that he is not a plagiarist. With regard to your second question, the thing died after a couple of sessions. I think that Hooke got this out of his system. They had the first meeting where he said Newton was a plagiarist. It's in Hooke's diary, so you can actually see Hooke's own account of what they discussed in that first meeting. And it is about the wave versus particle theory of light. It's about some of the experiments that you find in micrographia, which Newton has, of course, built on in his own optical work. He's built on it, but he hasn't plagiarized. How many were part of that? Sorry?
How many were part of that?
What, the group?
The rival society, yeah.
I think only about 6 or 7. I mean, they're his mates, but they include Christopher Wren.
Was there a tension between Newton's hostility to the public sphere and the philosophy of the Royal Society, which depended on experiments, etc., being witnessed by other people?
Yeah, I think that there's a big tension. I think Newton can't handle being part of that group. You're absolutely right that the philosophy in that space of the Royal Society depends on the very things that he detests. I think he can't suffer being there for very long. That they require degrees of what in the jargon is called in-principle replicability. So that they demand that somebody write in a way that makes it easy for people to either see how things could be reproduced, replicated, or to be able to actually reproduce, replicate them themselves. And that requires describing things in a particular way, like Robert Boyle, where there's a virtue of tedium. Boyle has people draw images of real air pumps, of real experiments, things that actually existed. So this is the Aristotle. So this is this world. Boyle is an Aristotelian in that sense. This is this world. This is what actually happened. Newton's not. Yet Newton's accounts of his experiments are diagrammatic and idealized, and people cannot reproduce them. That's part of his problem. And he's not about to write things tediously, as he says. He's not going to do the tedious line, because that's not proper natural philosophy. He wants absolute certainty, and you don't get that from having hundreds or thousands of people warranting what you've done by reproducing it. There's something inherent to the argument that you either get or you don't get. And if you don't get it, if you don't agree with Newton, you are essentially saying, the line from Newton is you're saying that I'm a liar, or you're saying that I'm incompetent. So go for it. Which one is it?
And yet Newton became the president of the Royal Society?
He did. But the Newton's presidency in the Royal Society is from 1703 to 27, in which, by the way, he supervises a number of extraordinary experiments from Francis Hawksby and others on hydrostatics and so on. But the sort of predilection for mathematicism in that moment is a sort of brief point in an unbroken sort of medicalized empiricist approach to British science that goes from 1660 to 1820. There are periodically efforts to overturn what people take to be bad natural history as the foundation of natural philosophy. But you've got somebody like Joseph Banks, who's president from 1778 to 1820. And Banks's view of the world dominates British natural philosophy for that period, for over 40 years. So the sort of mathematicist view doesn't come in until the 1820s and 30s into the Royal Society. But there are other avenues where people can do science in Britain.
One last quick question. Yes, gentleman in the third row from the back.
You've noted that in some way the Newton could have, ameliorated some of the problems with regard to plagiarism if he had immersed himself, if he published, then it would have helped to demonstrate priority. But the wider question, I suppose, about the vitriol, the ad hominem arguments and so on, was there anything that could have been done there, do you think, or was it inevitable given the personalities of the men concerned?
There's no one to rein him in. I think that's a problem. He became extremely powerful very, very quickly. And when he doesn't get his way, he takes his toys home and does his thing. Obviously, it's a fascinating question as to whether things could have been different. And you can see at the start of 1676, Henry Oldenburg does a great job of getting him to write this letter to Hooke, which is just a brilliantly done letter, which looks in one or two sentences like he's being genuinely paying homage to Hooke, and then in others he's saying, I've seen further than you. What you do is deeply problematic. And then, of course, Halley deals with some of this in the summer of 1686 and manages conversation in London to Hooke's disadvantage, because he's dealing with a very sensitive man who has had enough of Robert Hooke. And there's a wonderful letter that he writes to Halley. It's an addendum to a letter in June 1686, where he goes, to use a phrase, he goes off on one about Hooke and lists all of the slights that Hooke has done over many years. And it starts off, "Is this not very fine?" ? And he just goes through and destroys any claims Hooke has got. But that's how intellectual property disputes go. You know, he was prepared to give Hooke some credit, but now he goes through the Principia and crosses out Hooke's name, because that's what happens. You upset me. I'm now going to take you out. That guy's not going to change. He's still an angry young man when he's 83.
Great. Thank you very much indeed, Roger. Thank you for our listeners.
Good afternoon, everyone. Welcome back to the afternoon session. The first speaker of this afternoon is Professor Reinhard Werner from Leibniz University, Hannover, on Bohr versus Einstein. Please take it over.
So thank you very much. It's an interesting venue for me. I'm a physicist. Actually, I'm not going to apologize for the Leibniz in the name of our university. But the other interesting thing there is I'm a mathematical physicist working in quantum information theory. So I'm not a historian at all, and so you will see that I'm taking liberties that historians shouldn't, like taking sides in a debate. But of course, if you, well, we can talk that out. So, okay, so these are the two people that we are talking about. So we have Bohr and Einstein. Einstein was a little bit older, also died a bit earlier. Here is a picture of the two of them a little bit at a slightly older age. And some of the famous pictures we have, there are not so many, of the two actually together on the same picture. So this one is particularly famous, sort of like the icon for the Bohr-Einstein debate. So let's maybe put that into a temporal perspective. So I marked here, well, the horizontal line there is 1900. You see the units. I'm a physicist, you see. So one of the remarkable years here is, of course, Einstein's so-called annus mirabilis, 1905, when he wrote 3 fundamental papers. Well, actually more papers than 3, but 3 of them were really famous and changed a lot in physics. And then, of course, in 16 we have general relativity. So he was clearly one of the most creative theory builders we had in that century. Bohr is known for the model of the atom, that is 1913, and also for his notion of complementarity that will actually be also part of this talk. So right away, I think I should comment a little bit on the research style of these two people, because they were almost diametrically opposite. Right? So with Einstein, you could say he was his great superpower, if you want, was this ability to detect clashes between physical principles, also between different theories. So the 3 theories that he was talking about in 1905 were the 3 big theory groups of his day: mechanics, electrodynamics, and thermodynamics. And between any 2 of these, he found a clash of principles and resolved it, or at least addressed it in an interesting way. So, for example, famously, the clash between mechanics and electrodynamics that he detected led to special relativity. Right? And similarly for his work on Brownian motion and on the photoelectric effect, which was one of the founding observations of quantum mechanics. So Bohr didn't work like that at all. In fact, if the Bohr model of the atom, every physics student at the time would have known if an electron is whizzing around the nucleus, as in this model, it should radiate like hell. Right? electromagnetic radiation. And so this was clearly one of the known principles of the day. And what did Bohr do? He said, well, let's just ignore that for a while. Now, this is a move that would be totally against Einstein's grain. Right? He would never have done that. But all the more, but it was successful in a way. Right? So not only did it get the spectral series right, but also worked still for the isotopes, right? for heavy water, heavy hydrogen. And they predicted the correct spectral shifts there. That was a bonus that nobody could have foreseen somehow. And so clearly people saw that there must be some truth in that. And so Einstein acknowledged that and was always very, very impressed by this work of Bohr, because in a way it was something that he never would have done. So let me go on these matters of style a little bit. I mean, one thing is certainly this whole debate was very polite. And they always had great respect for each other. Actually, in reading up a few things on this for this talk, I came across an exchange of letters when they both got the Nobel Prize, and they were, well, Einstein got it first in 21, but the awarding ceremony they shared in 22. And so Bohr was writing that it's great that you got it first because I couldn't have lived with you not getting it before me, or something like that. And they were very polite to each other, right? So that's one thing. Their writing style is markedly different. Einstein was brilliantly clear in whatever he said. Right? So you can read Einstein and there's no misunderstanding him, I think, or at least very little. Whereas Bohr is almost impossible to read or to extract a clear meaning from. Actually, he said at one point that he thought that truth and clarity were complementary, which in his language means that if something is clear, it can't be right. And so I think that's well, I don't like that attitude very much anyway. So also, Einstein was completely up to the technical tools of theoretical physics of the time. With Bohr, that is a bit dubious. He was always praised for his intuition, like he could arrive at a conclusion without even doing the computation. Well, opinions vary whether he would have been able to. Right? So also they interacted with the community very differently. Bohr was very politically minded. Right? So, for example, it was very important for him that the theoretical physics community would speak to the outside world with a clear, unified voice, and he didn't mind if it was his, right? Whereas for Einstein was always Einstein always kept out of organizations, and so there's one statement where he said, the only community I ever want to be part of is that of the people who are searching and trying to find out and understand things, and saying in the same quote actually that he believed that was only a handful at any given time, right? So it's a little bit elitist, but anyway. So, okay, so they were different in that way, but they had a common thing also, namely that both were very influential in this process leading up to quantum mechanics. So let me put the timeline on again. So the whole process of guessing and finally arriving at quantum mechanics started maybe in 1900. It's a nicely memorizable date with Max Planck. And then there was all this period of guesswork, and they both had had by letters, and actually Bohr gave regular survey talks on the current status of atomic theory, or whatever they called it at the day. So they were both very had strong influences in this community. And then the big thing happened between 25 and 27. It depends on who you talk to and what they put as a starting date, or maybe even the starting place. There is a little booklet around by Carlo Rovelli called Heligoland, where he says it's not just 1925, he can also name the rock where it happened, right? So anyway, I think that's a bit exaggerated. But this was a very, very short period, and within that extremely short period, the theory was formulated and mathematically worked out. Actually, one of the underrated people here is this guy, John von Neumann, who basically created the theory, or well, at least the formalism of the theory, right? Okay, so let us come to the Bohr-Einstein debates. So these are again, the same timeline, the encounters they had. So I will talk a little bit about in 1927. So that 1927 is after the birth of the theory. Heisenberg's uncertainty paper was out, von Neumann's mathematical structure of quantum mechanics was out, and Bohr was giving a lecture at a conference in Como that Einstein didn't attend. And then they both were a little bit later at the Solvay Congress in 1927. And there's a remark by Einstein that I will comment on about the meaning of the wave function. So this is the first meeting, and they had big discussions here. I call that the round one of the Bohr-Einstein debate. Then there's round two, which is in 1935, triggered by the paper by Einstein, Podolsky, and Rosen, short EPR, about, well, problems he saw in quantum mechanics, and very famously a reply by Bohr. I will definitely comment on that. So these are the two main events of this Bohr-Einstein debate. Okay, so let's have a look at the topic. So what was the debate about? And one way to put it is to say it was about one of these principles of Einstein that he was so great at, right? So one of the way he wanted theoretical physics to work, and this could now be summarized under this heading of local realism. That's actually a term that was coined later, but I think it fits pretty well what Einstein wanted. And so the idea is that if you build a new theory, and they were just building a new theory, quantum mechanics, then the first thing you should do is find how to describe your system. What are the variables, the mathematical objects that you use to encode what the world is like, right? And this kind of description should give you, provide a language so you could talk about the real factual situation in some region of space-time. That's actually a phrase that he used, so it's in quotes. Not that early, but he did use it, right? So, and part of this idea is that, of course, Einstein created relativity. So this causality idea was always there. That is, if the real factual situation in one place should not depend on what somebody else does far away, right? And relativity has a very sharp notion of what it means far away. That means that no light cannot be connected with a light signal, right? So, so there is a locality part of it, and of course also you would like to see dynamical laws that tell you how the state changes, right? Okay, so this is the ideal of local realism, and one has to say that all of classical physics, classical is of course just a term to say pre-quantum in this context, right? So all pre-quantum physics works like that. So it was an abstracted principle from the way all physics at the time worked, right? So it was not just invented for the purpose. But he had this. He would be one of the few who would actually see that as important and formulate it and say that this is how things should work. Okay, so these variables that you have to find might not be totally obvious. So this Einstein's realism, if you want to call it that, is not naive in the sense that you just look at nature and then you see how to describe it or so. Right? You would have to just invest some serious work. So in his later work, when he tried to build an account along that pattern for quantum phenomena, he writes to Schrödinger that he's now trying overdetermined systems of nonlinear partial differential equations as a mathematical background that might do it. So he was really thinking about something that you have to, some mathematical structure that you have to create, and that might be totally non-obvious to the eye, right? Okay, so this is the quote. The reality is not handed to us, not just given to us, but it is like a riddle. We have to uncode it. You have to find the right description for it. Okay, So the counterposition to that would be this maxim that theories should be built on observable facts. Now, to begin with, this is not a direct contradiction to the other one. But in quantum mechanics, it sort of is, because we don't directly see the quantum particles. So there's no level where you can see the description of a reality and what we see of it are not somehow obviously connected, right? And of course, in some way, the whole debate is about that. So it's not a direct contradiction, and it is actually a very early position from the Copenhagen side, if you wish. So this is actually Heisenberg's principle with which he starts in 1925, that the theory should be built on observable facts, and at that moment, this is directed against Bohr's model of the atom, because the orbits in the atom are something that you can't see directly, right? Because if the atom doesn't radiate, how would you know that the electron is going round in a circle? So he says we have to look instead at the interaction with light, and he comes up with these matrices, right? So, and then also later in 27, he actually follows Einstein in his work on relativity. So the way the first relativity paper is written, he says, well, if we look at the idea of simultaneity, equal time relation, and we do this under the conditions that there is an observer-independent speed of light, that is the same for every observer, how would synchronization then work? How could this concept even work? And if you work a bit, well, quite a bit, then you end up with relativity in a pretty straightforward way, right? So this kind of analysis that some people would also associate it with the style of Mach, Ernst Mach, he came up with relativity, and Heisenberg is trying to be the quantum Einstein, right? So definitely in the 27 paper, he does that very explicitly. 27 is that's a paper on uncertainty relations. So there's this passage in Heisenberg's autobiography where he relates the story that he met Einstein after doing this work, and so the young man, he was, how old was he? Like 24 or so, right? So he's going to Einstein and say, I applied your principles and I came up with this brilliant new theory, right? And Einstein was not impressed. He said, well, this is good. I may have said something like that you have to start from observable facts, but was kümmert mich mein Geschwätz von neulich? So what, no, he didn't say that. But I say a lot when I don't think this is true at all. Instead, he says, the theory decides what can be measured. Now, if you want to put that in this context of this debate, in this idea of local realism, then what he is saying is, if you understand the right variables of the theory and the dynamics of the theory, there is no separate measurement problem. This will automatically follow, right? You just follow the dynamics of the process that will involve also the measurement devices, and therefore everything is clear, right? You don't need any starting point from the measurement process. Okay, so this is actually what you could call the classical view of measurement. Measurement in that classical view is something that uncovers a property of the system that is already there somehow. And that is something that, well, in quantum mechanics we have become wary of, right? So, but that is basically what is behind this. Now, also in this counterposition is Bohr's notion of complementarity, which is that what classical concepts can be applied to a certain system? Like, does it appear to us as a particle or as a wave? That is, in the early days, that is really the distinction, is decided by the experimental setup. If we make an experimental setup that is wavy or sensitive to the wave nature, there is no sense to even talk about the particle nature of the particle properties of the system, and conversely, right? So the experimental setup decides. So this is exactly this start from the observations, from the operational description of what we do in the lab, and that sets the concepts that we can use to understand the system. And of course, this introduces a fundamental role for the observer. In Einstein's local realism picture, the physicist doesn't appear in any form, right? You talk about the world, and you don't care whether there are physicists around or not. Here, in some sense, you have to care about it. Okay, God, I'm late. So round zero is this story about what is psi, and this was at the Solvay Congress. It's a short remark that he makes and says this wave function that came up in the Schrödinger's equation was one of the key mathematical elements of the theory. How do we understand it? And he presents two options, and they are pretty much along the lines of this debate. One is, well, this could be the description of an individual system. Pretty much in the way like the variables that we have been looking for to describe quantum systems, that might be this wave function psi. Einstein always calls this the orthodox view. This is what he perceives the Copenhagen people are saying or are trying to do. And he has a problem with that. I have to go a bit faster now. So then if the wave function has something to do with the clickishness of the system, like the ability to trigger a detector, then if you have already seen a click, then everywhere else it must be zero. And this is kind of a non-local effect, but that only is a non-local effect if you believe that the wave function is a thing somehow, is a real physical field in the sense of local realism. The counterposition to that is an ensemble view, where the wave function is something like a probability distribution. And well, it describes a set of similarly prepared systems. So in that case, the collapse is just an update of a probability. You can do it in the evaluation stage of your experiments, maybe decades later. It's nothing that happens actually in the lab. Okay, so just for a cartoon, in the ensemble interpretation, the psi is something that relates to the preparation of the system. Of course, there will be a measurement to complete this whole experiment, but the psi would be about the preparation. And this is basically the minimal statistical interpretation that is quite sufficient to do everything in quantum mechanics or quantum information. The individual state interpretation puts it to the particle. So there is electron Joe with his own wave function coming along, right? So this is the different way of thinking. It's about the individual state, the individual system. That's what he calls the orthodox view, and many physicists are fuzzy about this distinction, still now, right? Actually, one recent debate calls this the epistemic view because it has something to do with what we know about the system. You could phrase it like that. And this is about what the system is. That would be the ontic view of the wave function. Okay, so I'll go a bit faster. Here's a quote from Einstein that really makes that distinction. Just very briefly, of course, he famously said that God doesn't play dice with the universe. And that is related to this thing that whenever you invoke probability, a probability distribution is never a physical field. It's something that depends on the whole way you set up your experiment. If you look at the probability distribution for a Brownian particle to be somewhere, it depends on where you started it. And it will be updated if you've seen it on the way in some other place. But nothing changes at the point where you're evaluating the probability. It's always about the entire situation. And so this introduces some kind of a subjective element that Einstein feels has no place in a fundamental theory, although he's much better at probabilistic theories than all of his colleagues, right? In 1905, he wrote one very probabilistic paper, right? Okay, so Bohr said to this, but it cannot be our task to tell God how to run the universe. This is actually one of the things that I wholeheartedly agree with because, yes, Einstein was trying to implement a physical principle, but then sometimes we do have to give them up when we are forced to by nature to do that. Well, they say God, but it really it's nature. Okay, so the Solvay Congress debates. I'll go quickly over that. So the narrative here that you find easily is that in these congresses, Einstein would, this is not in the proceedings because it was all over meals, right? or other meetings outside the conference room. So for breakfast, Einstein would propose a thought experiment refuting the uncertainty relations. And then by the evening, Bohr would have a refutation, and they would talk about that. Right? Now, this account is, on the one hand, by Bohr's own long account in the volume put together in '49 for Einstein, and there's a short paragraph in Heisenberg's autobiography describing it, and the only contemporary source that I know, there may be a few more, is a letter from Ehrenfest to Goudsmit and Uhlenbeck. I've quoted it here, so it actually tells the story. Let me just go over it quickly too. But the perception that Bohr won this debate is basically from these sources, so they're written by the winners, right? And I know that as a student, I read this stuff. I said, "What the hell are they doing? This is like a non-English person going to a cricket game, right? Everybody cheers, and you just don't know why, right?" And so this was. I was actually confused about this, and I think I can tell you that a little bit better now. It is about what they're doing here. They're playing a game of semi-classical physics, and that has some rules. So it has nothing to do, or very little to do, with quantum mechanics. That is what was confusing me. Right? Quantum mechanics is post-26 quantum mechanics, of course, for me. And then Bohr had, so you would mix wave pictures and particle pictures, and somehow arbitrarily switch between the two, and connect them with the Bohr relations. That was sort of the style of it, right? And then, yes, you can weasel your way through. That is what Bohr actually did, quite successfully and not stupidly. But really, this is a theory mix that is less than half-baked, right? It doesn't give you anything like an interpretation of the modern quantum mechanics, that is the post-26 quantum mechanics. And it did allow Bohr to remain a quantum guru without actually learning the new stuff. That is maybe a bit harsh, right? But there's actually very little evidence that Bohr mastered modern quantum mechanics ever. So he was always staying in this so-called old quantum theory. Okay, so yes, so Heisenberg also worked like that, and not very successfully. Oh, well, okay. So my reading now is that Einstein was railing against this inconsistent mix of things, where you would have like this is like double think, right? You can use both pictures, thanks, but really there's no criterion for when to do what. So okay, so let us go to EPR. So this is the paper, and this was written by Einstein and Podolsky and Rosen to combat this view that the wave function is like a variable in the sense of local realism, that it describes an individual system in every way. So this is what they call completeness. Right? The completeness would be like the role of this variable as such a description, as in local realism. And so here is the wave function is cited in the abstract and so on. And so the new element in this is that they look at correlation experiments, and that is very clever. That is definitely what what we are using these days in entanglement theory and quantum information theory and all that, right? So if you pick the right source and the right measurements here, then you have that they're maybe fully correlated between Alice and Bob. That is, whatever Alice measures, there's a corresponding measurement on Bob's side, so that these will be 100% correlated in their outcomes. So in other words, you can find out stuff that would happen at Bob's by measuring at Alice's side. This completely eliminates this sensitivity, this perturbation aspect. This is actually the uncertainty relations. And so this is why this is an interesting situation. The argument is that in this situation, you can compute what kind of state should describe Bob's system, and you think that this should be a real ontic state, describing the real factual situation there. But then this choice would depend on what Alice was measuring. So it depends on a faraway thing. So it is not local realism. Right? So that is basically the EPR argument. Of course, there's more to it. But so how was that done in the community? Well, I'll go over this quickly. So there was this nice phrase by Schrödinger that they all found it wrong, but only because they had learned their Copenhagen credo in unum sanctum. So my Latin is a bit rusty, actually like 60 years rusty. But it would be una sancta ecclesia normally, right, in the credo. But here it's male, so it really says that all learned their credo according to the saint who can only be Niels Bohr, the one saint, right? Anyway, so this is a letter to Pauli, and Pauli writes to Heisenberg, Einstein once more made a public statement about quantum mechanics. It is well known that it is a catastrophe every time that happens. I want to grant him that if a beginning student would raise such objections, I would consider him fairly intelligent and promising. How patronizing can you get, right? This is really... And then he suggests to Heisenberg, whom he's writing, that somebody should, take care of that, right? Clarify authoritatively that this is nonsense. And Heisenberg's, so I don't know the response to this one actually, but the Heisenberg's response is known. So he said, well, Bohr is already doing it. So here's Bohr. Bohr's reply appeared in the same journal with the same title and the opposite answer, which is, it's that, let's say it's a level of polemicism, what's the word? Polemics, it's a level of polemics that is definitely very unusual in a physics journal. Right? You don't have that. This is really bad style. Right? You wouldn't actually, nowadays people would just cross it out, but this was Bohr, right? So he got away with it. And here is a description of his then assistant, Rosenfeld, what he did. Right? So Einstein's problem was reshaped and its solution reformulated with such precision and clarity that the weakness in the critic's reasoning became evident. And their whole argumentation, for all its false brilliance, fell to pieces. It was impressive to watch him thus at the height of his powers. He was particularly well served on this occasion by his uncommon ability to go into the opponent's views, dissect his arguments, and turn them to the advantage of the truth. I don't know how you feel about that. I think this is utterly embarrassing hagiography, right? So actually what he's suggesting is that false brilliance means that they were intentional deceiving in this other paper, and they were not after the truth, right? So which is, I think this is, Rosenfeld should be ashamed of himself. Now, actually, this is the abstract of the paper. So Bohr claims an essential ambiguity in the paper. Actually, he doesn't name an ambiguity in the paper itself, and he uses the word essential only to emphasize places where he has no argument, right? Then of course he is advocating complementarity. Actually, three quarters of the paper are a lecture on complementarity. And now I would like to draw your attention to this last line here. So he says that complementarity fulfills certain demands, but he doesn't say that it fulfills the demands. It would seem to fulfill. Well, not even that. It would seem to fulfill, but only within its scope. So he was stepping on the rhetorical brakes 3 times, right? And then he pulls out the sledgehammer and says, well, this is about all rational demands of completeness. So who wants something else now is just being irrational, right? This is typical Bohr, right? So this mixture of pontificating and extreme caution in the formulations. So actually, he completely ignores the new aspects, actually transforms them away in a footnote on page 1, the only place where he actually uses formulas. Totally misses the point of the paper, of the APR paper. Actually, from the response, it's not clear that he read the paper even. We know he did, and he probably thought about it a lot because his whole complementarity philosophy changed in 1935. Yeah, so he clearly took a message there, but you wouldn't know from his response. So he has this lecture, and actually, one way to highlight the quality of this writing. In the collection by Wheeler and Zurek, right, Quantum Theory of Measurement or so it's called, a red book that was on many shelves, 2 pages had been transposed in the reprint, and nobody noticed. So this is just as an indication of the stringency of this argumentation. Okay, so, but the effect of Bohr's reply was this. Case closed. And actually for 30 years nothing happened. Well, almost nothing. I could name a few things, but really nothing. And the reason is that, you see, Pauli's suggestion, somebody should get rid of that for us. That is exactly what happened. This was the golden years of quantum mechanics. All these young, highly motivated, intelligent people who were just getting their Nobel Prizes by applying the new theory. They were just not prepared to listen to the old man who say, well, I have my doubts. Right? They just wanted it put away. And that's what happened. So after 30 years, we have this guy. And actually, this closes the debate. So this closes the debate about local realism. So actually, his argument is very elementary. It eliminates not just the psi kind of ontology, right? Psi as a mechanical variable, as a local realistic variable. He kills any kind of local realism, provided a certain quantum prediction was verified experimentally. So he actually opens up the possibility of an experimentum crucis, which is very, very rare in science, as all the historians here will certainly confirm. Right? It's very rare that you can make one experiment definitely deciding a matter. This is one, and that is the last year's or this year's Nobel Prize for actually experimentally doing just this verification. Okay, so I'm at my summary here. So I've restated the question. And so this is about the people. His contribution to this debate, Einstein's contribution to this debate, was to even state the problem clearly. And this he did very efficiently, and also made his contributions like the EPR paper. Bohr was actually not part of the debate in some sense. He was the figurehead for this whole quantum community that was emerging. They had delegated this whole debate to Bohr. And he did it, well, maybe to the best of his abilities, but they were not great. And so of course, this is a common debate now, like how much can we credit to Bohr? How much understanding was there actually? There are some very negative books like Marabella's Quantum Dialogues, maybe some of you know that. It was very bitter on Bohr. Actually, I spent a couple of hours at Blackwell's yesterday, and on display there was a book on Bohr's vision of physics by a guy called Perovich that I didn't know before, and I had a look at that. I'm all prepared to look at more charitable readings of Bohr, but it's hard to do, and it's very frustrating if you do it yourself. Okay, so the outcome of the debate in my summary is in round one, the general perception is Bohr won. I would say in the long run, this semi-classical complementarity that we're debating is now dead, really. You cannot do anything sensible with it, as if you ask me at least. Now, round two, the 35 round, was basically ignored by everybody. So the public perception wasn't even there. But in the long run, clearly, the result is that Einstein's view of local realism was refuted, was shown to be inconsistent with experiment. Yeah, I'll leave it there. So thank you very much for your attention.
Thank you very much. So wonderful talk. In the middle, please. The gentleman in the middle.
Thank you for your talk. Very, very enlightening. Would you agree that Rosenfeld's quote that you gave was very typical of him? Very typical of Rosenfeld, sorry. He was a Marxist, and so he was completely certain in his political views, and he took that certainty over into physics too. He absolutely adored Bohr. Anything Bohr said was definitely correct. Anyone who didn't believe it, and he said this many times in letters or in print, was either completely mistaken or a fool. He more or less had a Newtonian view of opponents.
Rosenfeld was actually particularly bad about that, but also many other people in the community. There's this horrible incident where the young student, or a PhD student of John Wheeler, came up with what we now call the many worlds interpretation, right? So Everett was sent to Copenhagen to get a blessing, which they weren't actually interested in. So Wheeler dropped Everett in a really, really bad way, right? So this perception of Bohr as a great saint who would sort of residing over everything and so on was very widespread. So books like Marabella's are a bit of a pendulum going all the way in the other direction. The truth is bound to be somewhere in between. I'm also a little bit on the far side in the criticism of Bohr.
In the back, again, middle, the third from the back. Yes.
Thank you for that. That was fantastic. Correct me if I'm wrong, but I understand that towards the end of Einstein's life, he spent a lot of time working on theories of everything, unified field theories. Sorry. I understand that towards the end of Einstein's life, he spent a lot of time working on unified field theories. And my understanding is that this wasn't looked upon particularly favorable by a lot of the rest of the physics community.
Certainly true, right? But what it means by unified field theory is actually unification of electromagnetism and gravity. As far as I know, it doesn't involve the quantum side. But this was another research program, finding a local realistic description of quantum mechanics that was up till the end of his life. You could have thought it's a reasonable program. I think with a bit of more, you know how it is. Sometimes if you have to, when something doesn't work, you have to turn around and try to disprove it. Had he done that sometime earlier, he would have come up with a bell-type argument, maybe. But he didn't, right? So he was guilty of not trying to shoot it down, which is, I think, a reasonable, after a few decades, is certainly a reasonable thing to do. But until his death, Bell really completely kills this idea. And I think he would immediately have accepted that and seen that, yes, you cannot do this, right? But the unified field theory is a different project.
Okay, the second from the back, please, and then next, the gentleman in the middle.
You talked about the clarity of Einstein's writing, but I've heard that if you really want to understand relativity, you don't understand it from reading Einstein. You understand.
Sorry, can you repeat the last part?
You talked about the clarity of Einstein's writing,
yes.
But I've heard that if you want to understand relativity, you don't study it by reading Einstein, you study it by reading other people who read Einstein and then explained it more clearly. So can you comment on that?
Okay, so relativity is something that has been done many times over and explained from different point of views. Like there's a beautiful little volume by David Mermin called It's About Time, right? Okay, very nice. It's also a good book. So many people have done that, right? And there's a long row of people who have explained relativity in their own way, slightly differently from Einstein. But I would suggest you read the 1905 paper. I think this is quite clear. So, and also in this statements about quantum mechanics, to my reading, it leaves nothing to be desired. It's quite clear what he wants. So yes, relativity is actually quite easy to understand. And of course, there's also a big pedagogical literature about it. And yes, you could say that maybe Einstein is not the ideal presenter of it, but I think it was pretty good.
So the third from the front first, and then go to the back. That last question.
Yeah, hi. I wonder if you could just say a few things about what you, as a physicist, think that the death of locality means. I mean, from a philosophical point of view, I tend to think that it means the death of our sort of naturalized concept of space.
Okay. First of all, I did not say the death of locality. I said the death of local realism. Yeah. Locality is alive and kicking. So actually in this whole, I've been touring the country, various countries actually, in explaining the Nobel Prize. And one thing that you have to repeat again and again is that this so-called spooky action at a distance simply isn't there. Right. There is no action at a distance in this whole setup. You only get a superluminal signal or any kind of signal if you use the wrong theory, which is a local realistic one. And then you see that there would have to be a signal. But Einstein's position is that no, this just shows that's the wrong theory. So Einstein was not refuted by these experiments in that sense. Right? He never made a wrong claim about it. It was a research program that he tried to pull off. We now know it's impossible. And of course, all this whole quantum view of things is confirmed. But there is no action at a distance here. Actually, Einstein called it a spooky action at a distance. That was in a letter to Born. Eine spukhafte Fernwirkung, right? And the German phrase, even more than the English one, does not suggest Halloween spookiness. It says weird, right? Actually, it's not actually there. Einstein knows full well, and he's writing to his friend Born, who knows equally well, what he means by an action at a distance. Something that allows you to send a signal. And they're completely aware from the outset that quantum mechanics does not contain this. There's no way to build a telephone with superluminal signals on the basis of all this. So this is why he calls it spooky. It's just spooky. It's not even an action at a distance, right? So it's not a proper action at a distance. It's just a spooky one that seems to be there when you use the wrong theory. Sorry, I was... Is that clear enough?
Actually mean, what does it actually mean then? What does it actually imply for physical reality, if you like?
Well, first of all, it completely kills this notion of systems completely described by their properties. And because if you do that, you would get, I mean, this would be the classical part of the realistic part of local realism. If you do that, you get spurious action at a distance in your theory that you then have to explain isn't even there, because everybody knows it's not there. Right? It's experimentally and theoretically, everybody agrees. There is no action at a distance. There's no way to build a signal. So you get, when you use the wrong kind of theory, like certain Bohmians do, then you get some kind of non-locality in the sense of signals, but only in this wrong theory. So you have to live with that and realize that you cannot describe quantum systems by a complete list of properties, and that everything you find out by measuring is not just uncovering something, but introduces an interaction in this interaction your result will be generated. But it destroys whatever other properties the system might have before, so it's actually not sensical to even talk about these properties. Or it's not helpful. If you wish, you can, but it's not going to be a part of any explanation. Sorry, it was a bit long.
Let's move on to the last talk. Last question.
Thank you. That was actually more or less answered my question. I just wanted to say thank you for the fascinating presentation. You started by showing us how absurd Bohr's approach was actually, and how reasonable Einstein's criticism of this situation is. But unfortunately at the end you say, well, Bohr is right and Einstein is wrong. So even though Einstein's criticism and everything was justified and reasonable, he was wrong, and Bohr was right all the time, even though nobody actually understood what he was saying.
Okay, I would have to go over a few things again to respond to that. So there's early Bohr with this very simplistic complementarity viewpoint, which is basically about waves versus particles. And there's a later version of it, actually in response to the 35 paper, where he says, well, you always have to use classical concepts even if it's just to communicate the results of your experiment. You have to use a classical language. There is no quantum language that you could publish in the Physical Review. So, this is something that nobody can, I mean, everybody has to agree on that. That's simply true, right? So, but this milder form of complementarity is something that we're actually using all the time now. So this is this operational view of quantum physics where you do start from the devices. So in that sense, yes, Bohr was right. Not the early Bohr, certainly. He had completely crazy ideas, part of some of them. But this part that we are taking over, it's like Heisenberg's program of starting from observable quantities, but much more radical than he was. So we went this way. And it works perfectly and has been working for 100 years, right? So in that sense, yes, Einstein's vision, we had to give up this principle by Einstein. But Bohr was not very helpful in making that transition. Okay, in some sense he was right in the end. But yeah, he didn't contribute much to that. Yeah.
Okay, I think we should move on to the next speaker. So maybe during the coffee break, please ask the question. Let's thank the speaker again. Okay, so the last speaker of this session is Simon Mitton, University of Cambridge. He's going to tell us about the Big Bang versus steady states, with these rivals in cosmology. Please.
Right. Thank you very much. I am not a professional historian. I've got a physics degree, and I've been a science writer and had a long career as a publisher, as a few people in this room are already aware, because I've published you. So I like to speak in terms of people, their circumstances, where did they come from, what's their background, and then how did they interact with each other, and what motivated them. So you will see I will be talking about people rather than the specifics of their papers. And I've got four kinds of people. There's the three pathfinders, Einstein, Wilhelm de Sitter, and importantly, Georges Lemaitre. We've got two observers who are absolutely crucial in this story for data on realism about looking at objects in the universe and what they could find out. We've got the three musketeers, Gamow, Feuds, and Ryle, and I identify two jousting tournaments which they have. You will notice that I do not have Gamow versus Ryle. That is because neither of them met each other, and they didn't correspond. Some of this you've heard already, so I'll be very quick. 1905, we have Einstein's four papers. The road to general relativity was long and difficult. And so far as I can see, it wasn't until 1913 when Einstein learned and adopted Riemannian geometry and tensor calculus that he began to make rapid progress. In July 1915, Einstein met up with David Hilbert. Einstein knew that Hilbert was trying to find field equations as well. And in the course of this meeting, it seems that Hilbert realized he needed to get on with his program, which was not identical to Einstein's. And that led to a sort of desperate race against time for Einstein, who was worried that David Hilbert would get there first. So on the 25th of November, 1915, Einstein read his paper on the gravitational field equations in Berlin. Now, in some of the popular accounts of this, you will read that Einstein was close to a nervous breakdown and so on and so forth. He was also dressed in formal evening dress, as they did in those days in workshops like this at the Prussian Academy. 5 days after Einstein had completed and submitted his paper, Hilbert published a note giving the field equations, but the big in terms of priorities, the big difference between the two is that Einstein gave his proof, whereas Hilbert did not. Now, there's many solutions to the field equations, as everybody in this room is very familiar with that. Einstein in 1917, he is the first to apply the field equations to the entire universe. Now, in terms of what we've just been hearing about Bohr and so on, this is in some ways rather remarkable that Einstein is now going to apply it to the whole universe. Of course, he has to make assumptions about parameters. So Einstein produces a model which has no pressure, in other words, no radiation, but it does have matter. He didn't straight away consider its stability. It is a model which is unstable. Wilhelm de Stisse, he decided to look at a universe model which did not have any matter but did contain the radiation, and his solution too had difficulties. In 1922, Friedman in St. Petersburg, he is the first one to publish dynamical solutions, and he publishes them in Zeitschrift für Physik. He finds a solution in which the universe is allowed to expand and where it's allowed to contract. He makes no connection whatsoever to astronomy. The main impact, immediate impact, which he had, is that George Gamow, who was in St. Petersburg in 1922 and took Friedman's lectures, this is when Gamow first becomes interested in general relativity. The big step forward comes in 1927. Georges Lemaitre had been working on general relativity, self-taught, from probably 1919. And as part of Belgium's post-war recovery, he was given a big travelling fellowship to spend 1 year at the University of Cambridge working on general relativity with Eddington, followed by another year in Cambridge, Massachusetts, working, for example, at Harvard College Observatory, where he came across observational astronomy and so on. By 1927, he had derived solutions for the time evolution of the radius of the cosmos. In other words, the expansion of the universe. Out of loyalty to his country, he was very much a Belgian nationalist. He decided to publish this in the Proceedings of the Brussels Scientific Society, which is a journal that was circulated to libraries and so on worldwide, but it had very little readership outside Belgium. So nothing happened for a while. Then in 1930, he wrote to his former tutor, or his former mentor, Eddington, and Eddington suddenly gives him a lot of support. Eddington described Lemaitre as being the most talented student he had ever had, and he regretted immediately that he hadn't noticed the 1927 paper. It made such an impression on him that he got Lemaitre to London. Lemaitre spoke at the Royal Astronomical Society in 1930, and this resulted in the publication of his paper in translation in the monthly notices of the Royal Astronomical Society. The importance of that is the monthly notices had a global circulation through the British Empire and so on and so forth. And so very, very quickly, Lemaitre's ideas catch on. He did another very high-profile lecture talk in 1931, which was connected with the British Association for the Advancement of Science. And so this is when a wider public begins to learn of Lemaitre's work. We were just hearing about Einstein's approach to realism and so on and so forth, and he was at the Solvay conference. This was the 1927 one. Lemaitre, of course, wasn't invited to things like the Solvay conference, but Lemaitre managed to meet up with him in a coffee break, as it were, and said that he liked the mathematical elegance of Lemaitre's work, but as a piece of physics, it was abominable. Lemaitre did recover from all of that, and he recovered from it by promoting his hypothesis in picturesque language as a fireworks universe in which everything has a singular origin and it explodes with enormous violence, and so on and so on and so forth. The impact of this in terms of quantum cosmology is Lemaitre is the first one to find an application for quantum physics in cosmology. He was the first quantum cosmologist. He applied the phenomena of radioactivity and the uncertainty principle to the origin of the universe. Now let's do a bit of realism and consider the two people who found evidence for the recession of the galaxies. The first one is Vesto Slipher of the Lowell Observatory in Flagstaff, Arizona. He uses a 24-inch telescope with a spectroscope, and he starts to look at the spectra of spiral nebulae. There's a bit of a backstory here which is helpful to know. The Lowell Observatory is named after Percival Lowell, who was a Bostonian Brahmin, a person with a great deal of wealth, and he set up this observatory in Arizona and appointed an astronomer, went and observed there very occasionally himself. The purpose of the observatory was to search for life on Mars, and Lowell himself published 3 books, the third of which is all about the economic and social system which exists on Mars. So this is the person who was Vesto Slipher's boss. Why was Vesto Slipher looking at spiral nebulae? Because Lowell believed that the spiral nebulae were nearby planetary systems in formation, which was not an unreasonable hypothesis. Well, when Slipher measured the redshift of the spectral lines in the Andromeda Nebula, he realized straight away that it must lie outside our own Milky Way system. He went on with this program of measuring the spectra of spiral galaxies. He was in contact with the Lick Observatory, which was the other observatory in the US where this work could have been done. And they had a 36-inch telescope, and they wrote back to him and said, you'd better be correct in what you're saying, because we've been unable to reproduce it, and basically you're going to make yourself look a complete fool. Anyway, the complete fool published data on 25 spiral galaxies, got the gold medal of the French Academy of Science in 1919 and the gold medal of the Royal Astronomical Society in 1932 for this work on measuring the velocities of galaxies and showing that they were in recession. Edwin Hubble, he was looking at the Andromeda Nebula as well, but from a different point of view, and using Cepheid variable stars, he was able to establish its distance and find that it was far, far beyond the Milky Way. He and his colleague or assistant, Milton Humason, by the middle of the 1920s, they had measured the distances to 40-odd spiral galaxies. It was in 1929 that Hubble does the first of his velocity distance diagrams. These are linear plots in which the velocities, almost all of them taken from Vesto Slipher, and quite a few that Hubble used. He did not give any credit to Slipher for them. So the velocities basically came from Slipher, and the distances came from Hubble and Humason's measurements of plates taken with the 100-inch telescope at Mount Wilson. In the version of this diagram that was published in 1929, there were only about 14 or 15 points, and only an optimist would have suggested that it was possible to put a straight line through them, which is what Hubble did. But then he went on and got this, more accurate one. Interestingly, to me, Edwin Hubble never, ever claimed or accepted that he had discovered the recession of galaxies. He maintained, right until the point at which he died in 1953, that there could be other explanations for the redshift phenomena apart from the recession of the galaxies. Now, when we get to the Hubble Space Telescope, there's an enormous publicity operation going on at NASA, and they put out a great deal of information, misleading information, about how the telescope was named after the person who had discovered the expansion of the universe. In 1936, in the last sentence of Hubble's book on the nebulae, he says that he dismisses as airy speculation much of what is being talked about, and advises that this airy speculation will only cease when there is a lot more data. Already by 1936, Hubble and the people at Mount Wilson were hoping that there would be a larger telescope, and vague discussions about what the 200-inch were already underway. Lemaitre's quantum cosmology, Lemaitre publicizes this through talks and so on, and came up again with this picturesque expression of the universe having actually existed for all time, but existing just as a primeval atom which contained all of the matter and all of the energy, and it suddenly started to decay radioactively because of the uncertainty principle. he was the first person to use what was known as the Hubble diagram to actually derive an age of the universe. Very interesting character. And with the expansion of a very hot, energetic universe, he realized that there should be something left over, and he thought that the cosmic rays might be the relic of the fireworks universe, and he spent the last 10 or 15 years of his life working in cosmic ray physics. Okay, now I come to the three protagonists. George Gamow, theoretical physicist, born in Odessa. He had an absolutely terrible time. He lives through two revolutions in 1917, and then there is the rise of Stalin. There's also the Civil War in, I think, 1922, 1923, and he writes about that in one place in an interesting context. He's preparing for the examinations at the end of his first year studying physics at Odessa University. And he says that 4 blocks away, he can hear the White Army and the Red Army fighting from house to house, just sort of down the road, and he just carried on working. In 1923, he leaves Odessa and he goes to St. Petersburg. His father sold the family silver to get the money to enable him to go to St. Petersburg. And there, his career in theoretical physics absolutely takes off. He's influenced, as I said, by Alexander Friedman. He's also interacting with several young men who became very well known. For example, Lev Landau. And 1928, in order to improve his knowledge of the new physics, he went to Göttingen. He also got permission of the Soviet authorities to spend time in Copenhagen with Bohr's Institute. This is where he made a discovery that, as the historian Helga Krag puts it, just, but only about just, should have won him a Nobel Prize. This was the quantum mechanical tunneling, allowing a particle to penetrate a potential barrier to either get into a nucleus or get out of the nucleus. We know from Gamow's memoirs that this whole idea, from conception to writing a paper and sending it off, took him less than a week. He became increasingly dissatisfied with Soviet Russia. Stalin forbade the teaching of anything whatsoever to do with quantum mechanics in the Russian universities in St. Petersburg. This, of course, was because everything Soviet was predetermined. In 1933, the Solvay Conference, Gamow participates in the 1933 conference, and he decides that he will go to America and work there and not go back to Mother Russia. Right. So, I'll now come on to Fred Hoyle's early life, which is easier to deal with. Bingley, West Yorkshire, lovely accent which he employed to very great effect in the late 1940s and early 50s with his radio broadcasts. And his father signed up World War I, enlisted, Machine Gun Corps, served 4 years, came back alive, survived the Battle of the Somme. According to Fred, what his dad told him was, he survived the Battle of the Somme because it was very, very misty, moisty morning, and he just told the 5 guys he was responsible for, don't fire anything, don't fire in the direction of, and they survived because that's what they did. He went on to read mathematics at Cambridge. His first doctoral supervisor was Rudolf Peierls, nuclear physicist, who went off to Birmingham. Hoyle then had Paul Dirac, who was in the same college as him. A lovely arrangement. Fred felt he didn't need any supervisor, and Paul Dirac felt it was beneath him to supervise students. So that relationship worked very well indeed, and Fred was appointed a JRF at St John's in 1939. Then his wartime work was research on radar for the Admiralty, and that's where he met Bondi and Gold, about whom I'll have more to say in a moment. In 1945, he returned to his teaching in Cambridge. Now, Martin Ryle is very different to either of these. A radio engineer and became a radio astronomer. He came from a really distinguished family that could trace their origins to being serious estate owners, farmers, in the reign of Elizabeth I. So his father became Regius Professor of Physics at Cambridge. Gilbert Ryle was his uncle, so on and so forth. Ryle was educated at a fairly exclusive private school and went on to read physics at Oxford from 1936 to 39. September 1939, he joins the Cavendish laboratory in their radio group, but after only 8 months, he was signed up to go and work on radar countermeasures, particularly the design of antennae by the telecommunications research establishment, and so his war service was all done there. He had a really traumatic time. He'd only been running his group at the age of 23 for a few months when 3 or 4 of them who were testing equipment that Ryle had designed in a Halifax bomber, the bomber crashed and killed everyone, and Martin never ever completely recovered from the trauma of this. Now, how to connect the war work with radar and cosmology? Hoyle devised a method of measuring the altitude of an incoming fighter attack plane to make measurements, observe from the ship, and be able to get not only the direction, but also be able to get the altitude and the distance. You needed both of those, of course, in order to take protective measures. Hoyle was, as it were, mentioned in dispatches for the great effect of the pencil and paper method he devised, which could be used in real time at sea. And at the weekends, as is very well known, he, Bondi and Gold discussed cosmology. Ryle, his antenna designs and his designs of receivers and detectors was very important when he got back to Cambridge in 1945, because he was able to start straight away on radio astronomy and observing the sun. Gamow had an easy ride because he had been a major in the Soviet army teaching teaching meteorology. He was denied security clearance. So when George Washington University was cleared out of all the nuclear physicists who went and worked on the Manhattan Project, he was basically left twiddling his thumbs and working on the formation of galaxies. Gamow had been interested in the origin of the chemical elements from the 1930s and had published 2 or 3 astrophysics papers. The quantum mechanical tunnel effect, he realized fairly quickly this would give you a method of building the elements by them absorbing protons, neutrons, whatever, and building up the periodic table. Gamow decided not to do any research on this. He gave the ideas away to others who went on to show that maybe you could get nuclear reactions going. Yes, right. In a flash of inspiration, he proposed that Lemaitre's primeval atom could be where there would be the right conditions in terms of energy and heat, in terms of energy, for getting neutrons to be absorbed by the nucleus. And he promotes this from 1942. The idea was made to work by his doctoral student, Ralph Alpher, who first of all demonstrated that a cold Big Bang didn't enable you to achieve very much because everything was over very quickly and there simply wasn't enough energy content. Alpher then began working on his own on a hot Big Bang model in which the neutrons in the early universe would have sufficient energy to be able to penetrate the nucleus. And for good measure, he calculated the present-day temperatures as 5 degrees K. Gamow was never interested in the slightest in this, and in later years he tried to get Alpha to drop it. Crucial test of Alpha's model was, did it reproduce the actual observed reality of the abundances of the elements? And this diagram is taken directly from the thesis itself. As far as I can make out, nobody has ever showcased the actual diagram in the thesis before. So you're the first. You can see the jagged line going up and down. Those are Goldschmidt's natural abundances, and all the other stuff in the diagram is alpha showing on an overly complicated diagram how all of this could work. And he established cosmology as a real branch of physics. Unfortunately for him, Gamow grabs all of the publicity. The initial paper, Gamow says the authors are Alpha, Beta, and Gamow. Beta had nothing whatsoever to do with it. That was just false. Then he organised a grand parade in a room like this for Alpha's doctoral examination. and invited 300 people, including the press, and arranged for the Washington Post to have, and the New York Times, to have nice stories saying that Gamow, and his student, had found that everything in the universe was made in 5 minutes. Fred was the real pioneer of nuclear physics. Fred didn't believe anything about Gamow's synthesis in the Big Bang. It all happened too fast. So Fred's contribution was that by 1946 he published a seminal paper saying that the origin of the element could be accounted for by these particle fusion processes at a temperature of 3 billion degrees in the center of red giants. Crucially, Hoyle published this paper before Gamow and Alpha published their model of nucleosynthesis. Needless to say, Gamow had no time for Hoyle's paper because Gamow claimed to have already proven that you couldn't make the elements in an equilibrium, a slow equilibrium process, which is what Hoyle's was. So Hoyle, Bondi, and Gold, their steady-state universe, which is 1948, after Fred's nucleosynthesis paper, Gold asked the question after watching this extraordinary movie, which you can loop continuously, what if the universe is like this? And the three of them and said, well, let's just work it out. Let's just do the physics. How would it work? And so that's how the steady state theory with the continuous creation of matter actually began. And the way in which the steady state theory could be tested against the Big Bang is very easy to understand. In a Big Bang universe, the objects that you observe now that are a long, long way away, you're seeing early in the life of the universe. Therefore, they will not look the same, they won't be perhaps distributed in space in the same way as the objects that are nearby. The whole point about the steady-state universe is that the universe itself never evolves. It just expands and new matter is created in the void, and the new matter then makes galaxies and so on and so forth. So no matter where you look or when you look, it always looks the same. The acid test was going to be, does the universe evolve? And Martin Ryle is the person who set himself the task, as it happened, of testing this. He and his colleagues began constructing radio antennae for observing initially the sun, but then for looking at radio emission generally. We're in the late 1940s, which I like to refer to as the heroic age of muddy field astronomy. They set up their first, there were Ryle and Graham Smith, two future astronomers royal. Neither of them knows any astronomy at this stage in their career. They're setting up the antenna, and this is a Michelson interferometer. And with an interferometer, you can get the positional information of the radio sources in the sky. And so Ryle began to make the Cambridge catalogues of radio sources. His first catalogue had about 50 objects. The second catalogue had about 120. The whole time, there was this nuisance, Fred Hoyle, snapping at him and saying, well, I've got all these ideas, I can explain all of that. Very nice of you to have got all this data and dealt with horses trampling your cables and so on, but I can tell you what it all means. Well, Ryle was never having any of that. So the first result, the first dispute between them was when Ryle started saying he had discovered radio stars, and Hoyle, the consummate nuclear astrophysicist, said they cannot conceivably be stars, and that was their first big dispute. From his surveys, Ryle, with his radio stars, he remains convinced that these objects are all inside the Milky Way. Now, this isn't terribly surprising because two of the objects were supernova remnants. So certainly some of them were, but not the... Gold and Hoyle pressed Ryle to say these must be distant galaxies of a completely new kind. And this irritated Ryle sufficiently that he was able to get Gold off the scene and dispatch him to the Royal Observatory and be a nuisance there. Ryle also became very distressed in 1952 when Bader and Minkowski measured the redshift of the radio galaxy Cygnus A. And as he said later, I realized to my dismay that we were in the cosmology game, and he didn't really want to be there. The big clash is to do with the counts of radio sources. Now, Ryle's first two sets of observations, there was insufficient data and they weren't correctly analysed, so it was easy for Fred Hoyle to say, you haven't proved anything at all. We could just as well be in a steady state universe. Third survey is looking good, but Hoyle won't have any of it. He's saying by then, well, this man, his first two were rubbish. Why should I take this one seriously? So for the fourth, Ryle had a publicist. This sounds a bit like Gamow with Alpha's thesis. Ryle had a publicist, set up a press conference in a room like this. Ryle's here, showing all the results. Fred is sitting over there under a spotlight, staring at his shoes and wondering what's going to happen next. He got the shock of his life when at the end Ryle says, and now, gentlemen, Fred Hoyle over here is going to tell all of you why I am completely wrong. And Ryle sat down and Hoyle rushed out of the room. So that was one of their very big clashes. All of this steady state and Big Bang becomes resolved very suddenly in 1965 with the discovery of the cosmic microwave background radiation. So the relic radiation is found. The theorists at Princeton University immediately realize that what has been found is the radiation which Alpha had predicted. However, so much time had gone by that those few people who did remember it thought it was Gamow who had pronounced or predicted the 5° K radiation. He never did any such thing, and it took a long time for Alpha to get the proper credit. The proper credit didn't really happen until the end of the 20th century. But the discovery of the background radiation was absolutely the end for Fred Hoyle's steady state theory, although he didn't accept it very readily. He never accepted it. He was always looking for something else. And so I'm going to give you one conclusion, which is a bit different to what you see elsewhere. These feuds over the origin of the elements and the nature of the universe and so on, these feuds were acted out in public, and it was the first time that had happened for astronomy. Both sides were maximizing their use of the media, newspapers, broadcast media, and quite recently in a letter which Gamow wrote to Ralph Alpher in 1955, 3 pages of it, there was a curious thing in the margin, and I turned this round and there was a little cartoon diagram, and Gamow is just saying to him, hook up yesterday with Hoyle, BBC, NBC, I gave it to him real good and won. And that is the only fragment of evidence that we have that the two of them publicly disagreed with something, and Gamow thought he'd won. Anyway, I'll leave it there for now. Thank you.
Thank you very much for really interesting talk. Is there any questions? Second from the back in the middle, please.
Two questions. You said that Einstein praised the mathematical elegance of Lemaitre's paper but called it abominable physics. So if he praises the elegance of the maths, how does he justify calling it abominable physics? And the second question was, you mentioned it was suggested that Gamow should have got the Nobel Prize for quantum tunneling only just. What did that mean? What did that mean?
I'll answer both of those questions. If I may, I think the answer to your first question perhaps was given elegantly in advance in the last talk, in that Einstein had much stricter discipline on how to model the world than Gamow. Gamow was very much for being very speculative. Sorry, Lemaitre. Yeah, with Lemaitre, Einstein just didn't accept a physical model in which the entire universe begins from a singularity. Right? So on your question on Nobel Prizes, this can only be dealt with in a sense by personal opinions. People like Helga Krag, who I turn to as my go-to source, because Gamow didn't settle down and work through the implications of this model, he simply blabbed about it to everyone and let them all go away and work out the implications. There was no follow through. In the case of Hoyle, who did not share in the Nobel Prize for nuclear astrophysics, when Tony Hewish, Jocelyn Bell, and so on, the discovery of pulsars, which is a very well-known story, Hoyle wrote a letter to the Times saying that Tony Hewish had stolen his doctoral students' ideas and data. Now, 2 or 3 days later, Hoyle realized that he'd made an absolutely terrible mistake by criticizing a colleague in the academy in those terms, and and so on and so forth. The opinion of people who were been close to Hoyle, of whom I'm one, is that he just completely disqualified himself. He'd written, he'd written a letter saying the Nobel Committee didn't know what they were doing. So I think I've answered both of your questions. Okay.
The gentleman on the right, from me.
With regards to the almost Nobel Prize, in fact, it was turning that whole idea around to get the alpha particles into nuclei, or rather protons into nuclei, that Cockcroft realized, and then of course the Cockcroft-Walton accelerator was built because of that.
That's right, yes, yeah. Gamow realized very quickly that the process he was describing was reversible, but what you've just said very helpfully that's another example of how he didn't follow through on things.
In the middle, gentleman in the middle. And then the very bottom next.
Thanks. And thank you for the talk. I enjoyed the spoiler alerts. You said that when Ryle unveiled the results from the 3C catalogues, that Hoyle basically did a runner, didn't respond at all. Why didn't Hoyle come back with an argument basically along the lines that the catalogue just doesn't sample enough of the universe? We don't know what distance these go out to, and so you can't say anything about whether the universe evolves or not. This sample's too small.
There was one respect in which the sample, the third and fourth, the samples were large enough because the parameter that was looked at was something called the log n log s diagram, which is basically
the inverse 3 halves.
That's right. Yeah. It wasn't showing 3 halves. It was showing 1.8. So
Okay. Thanks.
It's the log n log s diagram.
Hello. Thanks for a fascinating talk. You mentioned Gamow's colleague Alpha, did you say?
Yes.
So Alpha computed elemental distribution.
Yes.
Happening at the Big Bang.
Yes.
And then, as I'm aware, Hoyle proposed the alternative stellar synthesis.
Yes.
So but if I saw that correctly, Alpha's distribution agreed very well with some published data. So what happened with that information? Was it kind of felt to be still useful?
Alpha continued to work on the theory and improving the theory for a further 5 years, but the reason why it would ultimately fail is because the time period in which everything had to happen was less than 30 minutes from the start of the universe to the point where it's expanded sufficiently that you can't get any further nuclear reactions taking place. That was one difficulty. The other difficulty is that, which was faced by both theories for some time, not having any stable nuclei of 5, 6, or 7. This was something called the mass gap, you've got to get through it. The way in which Hoyle got through it was he said, well, actually, I'm not going to begin at the beginning. I know stars contain loads and loads of carbon, so I'm going to start with carbon and see what happens if alpha particles merge with carbon in the interiors of very hot stars. So he had a different approach altogether.
Very clever. And of course, people began looking at the supernova.
Yeah.
Every element. Thank you.
Is there any questions? I think it's very good time for coffee and tea. Let's thank the speaker again. There was a change in the program as announced from Oxford University. Stephen Brandel kindly take this summary talk, so please take it away.
Much, and thank you very much to everybody for staying for the final bit and of this extremely interesting day. It's a great pleasure to be here, and I'm standing in for Patricia Farrer, and I hope she gets well soon. So we've had a great day looking at feuds throughout history, and we've seen various different characters. I've got a few of them here on this slide. Of course, the Greeks, we don't really know what they look like, so we have just our ways of imagining them. Parmenides, we were hearing today that the only thing that exists is a sphere, so I thought the only way of drawing Parmenides was like this. Thank you. Similarly, Hooke, we have a lot of questions about what he actually looked like, because essentially all his portraits were destroyed, and maybe one that survives is possibly him. So he's known for his spring law, so I've had to improvise with that one. But the others, I think, are genuine pictures or paintings. So what have we seen today? Well, we've seen some very important myth busting. So Professor Anne-Marie Roux showed us that the idea that Galileo was essentially standing up for truth against the Catholic Church, who were persecuting him for having come up with heliocentrism, was a gross oversimplification. And that this combination of Galileo's personality and the way he went about that particular controversy was essentially what caused him to be tried by the Catholic Church. And the story we're often told is much more complex. We were also I think reminded by Andy Gregory. He did a very good job, I think, of persuading us that some of these long dead ideas associated with some Greek thinkers, that nothing does not exist and the only thing that does exist is spherical. You could kind of see the logic, and the way he drew out the fact that atomism was rebelling against that and saying that if you just alter the one proposition that the nothing can exist, then you end up with these, as he called them, Parmenidean atoms, these individual spheres that exist with nothing in between them. This idea of atomism was generated. He also, of course, explained this idea of Plato's triangles making up the world and making up all of the solids. And we heard about the connection between that, I think, in one of the questions, and string theory. Both of these are ideas that are pursued because of their mathematical simplicity. Neither Plato's triangles or strings theory are supported by any experimental evidence at all, so there is some potential similarity there. And then Rob Iliff showed us how Newton wanted absolute certainty. He hated hypotheses, he detested feuds, but his very nature led him into incredibly destructive feuds. And his ideas were decried by Leibniz as spectres of the imagination. And you think that must have hurt, given that he thought he was the one that didn't need hypotheses. He was working with absolute certainty and real truth. And then Richard Werner reminded us of the complementarity of truth and clarity, and perhaps demonstrated that Bohr showed you could be in a state of both total lack of clarity and yet not have found truth. And then finally, Simon Mitten described a feud which was about something incredibly significant, the very nature of the universe. What was at stake? Does it have a beginning? Does it have a finite or infinite age? And actually, he reminded me of this point that many of the early radio astronomers had come from the war working on radar work. And in fact, those people who were working on microwaves and radar, some of them here in Oxford founded electron paramagnetic resonance, and essentially turned that radar technology into looking at the micro world and condensed matter physics, my own field. In Cambridge, they turned them to the heavens, but they were amateurs, they weren't astronomers. And his talk reminded me of a talk I'd been to by F. Graham Smith, who pointed out in those early days when these non-astronomers didn't really know what they were doing, they built this radio telescope, their very first one, in a field in Cambridge, and it was a bit of a surprise to them after they built this thing and mounted it, that with radio telescopes you should really line them up with the ecliptic so that as the heavens rotate you can measure the signals. They'd lined it up with the hedge of the field, and it was perfectly parallel to the hedge of the field, but strangely that hedge was not aligned with any celestial coordinates. This is something that hadn't occurred to them. So I thought in this brief summary talk, what I might do is just bring a few things up to date and draw some of these threads together. So we heard about the ideas of atomism in the Greeks, and of course they were pitted, ideas of atoms were pitted against Aristotle and Plato. And in the early modern period, of course, it was Aristotle and Platonic thinking which was dominant and had become essentially entangled and conflated with Christian thinking. And so therefore, one of the problems with atomism was that it was mixed up with these terrible Epicureans who'd been after pleasure and wanting to fill their lives with pleasure, and this was definitely against the direction you wanted to go in. So in fact, it was Pierre Gassendi, a clergyman, who essentially Christianized atomism and found ways of reinterpreting that and realizing that you didn't actually have to reject Christian thinking in order to embrace the existence of atoms. Then it was people like Torricelli, and here in Oxford I have to mention Robert Boyle, who were working with vacuum pumps and actually making the void, actually making vacuums in their laboratories just along the high street here in Oxford, essentially founding chemistry, kinetic theory. Boyle was an experimentalist and somebody who embraced that kind of atomic thinking. So it started to come back into fashion. And it's amazing how late these ideas were still being debated. So around the turn of the 19th century, you have John Dalton in Manchester asking questions, as you can see in this quote here, about what's the nature of chemical reactions and trying to understand how atomic weight and the way in which chemical reactions combine can be explained through an atomic hypothesis. And Dalton came up with his ideas saying essentially all matter is composed of atoms. All atoms of a given element, they're identical to each other. They have the same mass, charge, chemical properties. Atoms can't be created or destroyed. What you can do is combine them together in whole number ratios to make compounds. And therefore you can interpret this idea of chemistry in terms of the existence of atoms. You can't see atoms, but you can hypothesize them and you can do calculations and it works. So essentially what Dalton was doing was sort of giving us our modern understanding of things like water being H2O, two atoms of hydrogen and one of oxygen combined together in a molecule. And here you can see in a molecular diagram. But it's amazing how late the resistance to the atomic ideas goes. So you have somebody like Berthelot, who asked the question, well, did anyone ever see a gas molecule or an atom? It's all very well having this atomic hypothesis, but you can't see them. So can you really be sure that they're there? And he points out that chemical symbols, you may use them to try and do calculations about chemical reactions, but they're dangerously subjective. The algebra of combinations is appealing, and of course the human mind is naturally inclined to substitute for a direct conception of things, which is invariably lacking, a simpler view in terms of descriptive symbols that, and my bold here, that give the appearance of more completeness. In other words, this is a way you can calculate things, but it doesn't really correspond to reality. That would be going beyond where we are. Wilhelm Ostwald, these are all great scientists who did wonderful things in their respective fields. Ostwald, we developed the theory of Ostwald ripening, which is very important in material science, and various other things. But here you can see him saying atomism is a doctrine that has miserably failed in any serious attempt to explain through mechanism all known physical phenomena. It's even less likely to succeed in tackling the incomparably more complex phenomena of organic life. And of course, we can laugh at that statement, as we know that DNA, we know its atomic structure, and this was one of the great triumphs of the 20th century. And it was people like Ostwald that gave this man a hard time, Ludwig Boltzmann. Ludwig Boltzmann was developing a theory of thermodynamics that had been developed in the late 18th and early 19th century and through the 19th century in terms of a thermodynamical theory that didn't make any hypothesis about atoms. It just looked at things like pressure and volume and temperature, looked at the relations between them, tried to understand thermodynamic systems, introduced ideas like energy and entropy. And Ludwig Boltzmann was trying to put it onto a statistical formulation, a way of understanding what might be going on at the microscopic level, which was consistent with thermodynamics. And he was developing the subject we now know as statistical mechanics. And one of the tenets of that theory is that atoms do exist. There is a microstructure underneath these thermodynamic systems. They really do exist in terms of atoms. And Ludwig Boltzmann got it in the neck from people like Ostwald and various other Feuds as well with Mach. And eventually he committed suicide, I don't think, primarily because of the attacks that he was getting, but they can't have helped. You can even find in a chemistry textbook in 1902 by Pure Duhem, and this is after a lot of evidence for the existence of atoms have come, not only from chemical reactions, but all kinds of things like the work of Avogadro. So here in a chemistry textbook, and again, another great scientist, Pierre Duhem, we know him from the Gibbs-Duhem relations in thermodynamics. Upon noting that the ease and clarity with which all principles of modern chemistry fall into place in a treatment excluding the name and notion of atom, one cannot help but think that the unique success of the theory of atoms is an illusory victory without future. And then, all things considered, modern chemistry does not support Epicurean doctrines. So it's incredible how late this is, that people are right in the dawn of the atomic age where radioactivity has been discovered. The quantum theory is just on the cusp of appearing. You have people railing against these notions. Now, it's often said that science advances one funeral at a time, and that therefore you need a generation of people to die off. But it's interesting how some of these ideas come round. So let's take this idea of the void that we've heard about so much today. One of the questions was, does it exist? And the Greeks were arguing over this, and Torricelli and Boyle, etc., say yes, they can make the void, they can make vacuums in experiments, and they can produce a volume of gas inside a glass vessel where they pumped all of the air out. In fact, their vacuums were not that great, but we now know, of course, you can make fantastic quality vacuums. But there was also this nagging question that we've heard alluded to in various talks today, how actually does Newton's law of gravitation work? Here was this amazing scientist that we heard about from Rob Iliff, difficult human being, but somebody who'd made extraordinary strides. He had this inverse law, a square law of gravity, that he argued over the priority of with Hooke, although Hooke essentially had just guessed a hypothesis. He'd shown how it was consistent with Keplerian notions. But how does it work? Because essentially all mechanisms in the 17th and 18th century all worked essentially on clockwork. You had to know how the mechanisms worked, how the gears fitted together, because we were living in a clockwork universe. And the kinetic theory of gases worked this way. Why is it you have pressure? Well, it's because of molecules bouncing off walls. You could develop that kind of theory. But how do you get action at a distance? How can the motion of the Earth and the Moon affect each other when they're separated by nothing? Where are the gears and where are the wheels? And so this is an interesting question about the void. Science apparently showed that the void exists. Of course, the modern view is we've almost gone back the other way, and we say actually the vacuum is teeming with activity. What you think of as empty space actually contains a soup of virtual particles coming in and out of existence. Forces are actually mediated by the exchange of virtual particles. So in a funny kind of way, we've wound things back and have said that the vacuum is more complicated than we thought. So it's interesting to see how these century, maybe even millennium-old debates are still continuing. Well, we've heard a lot today about feuds, and what essentially have these feuds been due to? Well, I think you can identify two main sources. There have been questions of ideas, really asking deep questions about physics. Did the universe have a beginning? Sorry, the university. Freudian slip. Is the universe, or indeed the university, made of atoms? And then, of course, questions of priority. Who got there first? Whose name should be associated with a particular discovery? And of course, you can see that these things are a strong function of personality type. Particular individuals in the history of science, as we've seen today, have become enormously sensitive about questions of priority, partly because it's bound up with their whole notion of who they are as people. And of course, because we've been doing the history of science and looking over that period, we've been doing a history of course, European white men. And I guess here perhaps the men is the most important thing. There have been a number of very big egos. So I kind of wanted to close today by just looking at a couple of examples of cases where it goes in the opposite direction. So one example we've heard a bit about today is Paul Dirac. Dirac was a complex man, in some ways a complex personality type, just like Newton, but in his case it produced a very different type of behavior. Yes, he was a highly individualistic thinker, somebody who was very much in his own world, someone who found it, like Newton, rather difficult to relate to other people. But in Dirac's case, he was not hostile and he was not disputatious. He was somebody who was actually very anxious to give other people credit. And just one example out of many. So I showed this facsimile of this quantum mechanics textbook from 1930, one of the first major quantum mechanics textbooks, not the first, but the most influential. And much of our language, the way we teach quantum mechanics today, is based on Dirac's terminology and the way he brought things together. One of the things he mentions in this book is this idea that had been developed only in the last few years at the time of all particles in nature being either fermions or bosons. Fermions are things like electrons and protons and neutrons. Bosons are things like photons, and we would also say the graviton and the recently discovered Higgs boson. And so everything in nature is one or the other. Now, the distinction between these two types of particles is the way in which they occupy quantum states. Fermions are gregarious. You can put lots of them in a quantum state. Bosons are a little bit like Newton and Dirac. Only one of them will go in a quantum state. And the statistics that they show, which means the way they distribute themselves around quantum states, is due to some theories developed essentially independently by Enrico Fermi and Paul Dirac for fermions, and Bose and Einstein for the bosons. And Dirac was the one who coined the term fermion and boson, and it's notable that he gives the credit to Fermi, even though Fermi and Dirac were working in one sense independently, but he gives Fermi the credit, and he gives Bose the credit for the bosons. And that's very typical of him. He refers to what we would call the Dirac delta function in his book. He, of course, refers to it as the delta function. And not all scientists behave in that way. Well, going back a bit in time, we've heard a little bit about Sir Christopher Wren. I wanted to mention him for two reasons. One is that he died 300 years ago today. So this is actually the anniversary of his death today. As Rob reminded us, it rather depends a little bit on which calendar you use, but on one of those calendars, if you use the calendar he would have used, it was February the 25th. So this is indeed the 300th anniversary of his death. He was the 9th Gresham Professor of Astronomy, and I'm married to the 38th. So that's another reason of mentioning this. Now, Christopher Wren was, of course, knocking around with a lot of the people we've heard about today, and he came up in Rob's talk. Christopher Wren was born at a rather difficult time because it was in his teenage years that the Civil War was raging. He was the son of the Dean of Windsor, so he was very much on the royalist camp because essentially he'd grown up in Windsor where his father had had a good living. His uncle was a prominent bishop. When the Civil War started, his uncle was sent to the Tower and spent the Civil War in the Tower. His father lost his living. Wren was associated with the royalist side because of that family connection. And in 1660, at the Restoration, you have somebody whose life has very much been shaped by growing up in civil war, where everyone was against everyone else. And trying to rebuild a society where you have to navigate disputes without it leading to pistols at dawn, as it were. And so Christopher Wren is a rather interesting personality type because he is very different from both Hooke and Newton. He's somebody who seems to have most of the time got on with absolutely everybody. Even people like Hooke. He was a great friend of Hooke. Flamsteed, who Rob didn't have time to tell us very much about, somebody who was enormously secretive about his astronomical records, not willing to share them with Newton or anyone else. Christopher Wren was involved in designing the new Royal Observatory at Greenwich and having to have lots of dealings with Flamsteed and also interacting with him. Flamsteed talks about Wren in glowing terms, even though he didn't get on with other people very easily. So Wren seemed to be somebody who could navigate these choppy waters. And just a couple of examples. So although Wren is mainly, of course, known as an architect, he did a lot of science. And one of his early bits of science was working on Saturn. He did many observations here in Oxford and also from London, studied Saturn over many years. And the big question was, what were these ring structures? Of course, we all know about the rings of Saturn, but they were very poorly resolved on old-fashioned telescopes. And Wren came up with a theory of what this was, and this was essentially his first big scientific publication. He thought it was some halo around Saturn, around the planet Saturn. And the issue is, as you go through the year, Saturn shows different bits of its rings to us. Sometimes they're edge-on, so it looks like there's just a line, which you can barely see. At other times, the rings are tipped back, and you can see this halo more prominently, what was going on. Huygens had another theory, which was the right one. Huygens came up with the idea of a ring. Once Wren had seen Huygens' idea, he wrote, he was just convinced by Huygens' idea, its natural simplicity, and this was a contrivance agreeing so well with the physical causes of the heavenly bodies that I love the invention beyond my own. So, here's a testament to the man that he could abandon his own idea because he'd seen a better one produced by somebody else. There was a bit of an argument between Huygens and Wren, because Huygens was actually quite a difficult character, but once the two men had met, they seemed to have got on reasonably well. And then, of course, we heard quite a lot about micrographia. This is a picture from Hooke's book, these amazing drawings. But it's interesting to note the preface of micrographia, because in fact it turned out that there could have been a dispute here, because the first person to do lots of drawings under a microscope was actually Christopher Wren. And in the preface to Micrographia, Hooke writes that he and of course it's the tradition of the day that you write a rather flowery preface, but he says he's reluctant to write this book because he was to follow the footsteps of so eminent a person as Dr. Wren, who was the first that attempted anything of this nature, whose original drafts do now make one of the ornaments of that great collection of rarities in the King's Closet. And then he goes on to say, Dr. Wren did affright me, for of him I must affirm that since the time of Archimedes there scarce ever met in one man in so great a perfection such a mechanical hand and so philosophical a mind. So, the idea in some sense of micrographia had come from Wren, but they were friends, and so Hooke could write something friendly about it. Now, of course, if you go into the modern age, there is an important development. So this is Heike Kamerlingh-Onnes, who's the person who first liquefied helium in the early part of the 20th century, and then went on to discover superconductivity. And one of the key things about why he won the race with Dewar is because he had an army of technicians, and here is Onnes with his head technician. And of course, this is something about modern science. It's much more collaborative. You have technicians, you have other people you work with, rather than just the lone individual working by themselves. You have teams of people. And one of Onnes's great gifts was not only that he was a good scientist, but he could work with other people and achieve great things. And that's something that is, I think, crucial about the development of modern science. Do feuds still exist? Well, yes, they do. So one feud that is going on at the moment is the question of room temperature superconductivity. Superconductors were discovered in 1911. It was a very low temperature phenomenon. Throughout the 20th century and the early part of the 21st century, the temperature below which you can see superconductors working, the so-called critical temperature, has been increasing year on year pretty much. But had got stuck at around 150 degrees above absolute zero. More recently, in the last few years, it's been possible to pressurize materials and achieve much higher temperature superconductivity. And a couple of years ago, in the journal Nature, room temperature superconductivity was reported, and this was seen as a great breakthrough. But there has been a huge dispute about it, and a few months ago that paper was retracted from Nature, and there is a dispute between two individuals, one who is criticizing these results. So disputes continue, and disputes in many ways are a good part of science because it's how science advances, by examining ideas and testing them and working out what is true. But it is nice when they're not hostile and when there is a friendliness and a generosity of spirit. So I think in that point, as we conclude today, I think it's important to remember that though feuds can sometimes allow ideas to progress, it's always nicer if people can do so more collaboratively and in a more generous spirit. So I'll finish there. Thank you very much.
Thank you very much for fantastic closing summary talk, also perfectly in time. I think we would like to take just one or two very quick questions if there is displayed. Very briefly, please, the gentleman in the front, the third line. There is no microphone.
You mentioned about the sort of action at a distance for gravitation. How is that resolved for magnetism? So there was magnetic ball that was occasionally there.
Yes, so with magnetism and electricity, the way in which we now would describe those forces being transmitted is by the exchange of virtual photons. So once again, there is a...
How did the Greeks deal with it? Because they had occasionally access to magnetic ore, and they studied it. They probably
Well, so the way the atomists did it is by atoms. So there are little atomic particles that go from one magnet to another, and they cut the air and they push the air out, and then the magnet is attracted and goes into the void. So yeah, you can read about this in Lucretius on the nature of things. It's beautifully done, and they have a mechanism for the whole thing.
Another display, just briefly, please.
What was the initial dispute between Wren and Huygens?
Between
Wren and Huygens.
Oh, so it was essentially a priority dispute. So the thing was, Wren had published his account and Huygens had published his account. And of course, there had been letters circulating. And I'm not an expert on this period, so I'm sure there are others who can say in more detail. But I think it essentially came down to, oh, in some letter, my ideas got leaked out. So it was the standard thing we were hearing about earlier today with conspiracy theories. You feel you're the only person to have had an idea. And it wasn't on Wren's side, it was on Huygens' side. But once they met, it was all fine. And Wren was immediately generous, as you could see from that quote, about saying, well, Huygens' idea is better. I stand back.
But how did they settle the argument about priority?
Oh, well, essentially, Wren just abandoned his claim because he said, Huygens' idea is better than mine. My idea evaporates, which is how things should be.
So I would like to thank very much again for the summary. And also to Joe for organizing this fantastic event today. Many thanks for this.